Hello, hi all. Welcome to the third day of the Improving Scientific Software Conference run by the Software Engineering Assembly here at NCAR. Today we're opening with a keynote. It's another historical one, but instead of kind of focusing on the hardware, we're kind of focusing on the software and what it was basically like as a software engineer a while ago. So I'd like to introduce Cheryl Craig, who was basically speaking from personal experience, has been at NCAR for 45 years, and we'll talk about life as a software engineer in the 80s, early 90s. Cool. All right. Thanks, Cheryl.
Okay, yes, as Jesse said, I've been here for 45 years, so I actually experienced this, the way we did computing back in the 80s and early 90s. I joined NCAR in 1980 as a student assistant while I was an undergrad at CU Boulder. I was studying math with a computer science emphasis. That was the best computer science degree you could get as an undergrad at the time. And I got hired to help a scientist organize his journal articles. Later, I did a lateral move after I graduated and joined a group in the chemistry division doing remote sensing. And so downloading measurements from satellites. So that'll come into play a little bit in my talk. And then after that, I made another lateral move and joined in CGD, the Community Earth System model working on CAM. And again, that will come up in my talk as well. So let's get started. Well, first off, this slide is too modern. Let's go with something that's a little more, carries the character of the talk that I'm giving. So let's go on. And as a disclaimer, I want to make sure you guys all know the content of the slide deck was me. I wrote what was in the slide deck, but then I used Gemini Nano Banana, that is their version, to beautify and enhance most of the slides. And if I've got time at the end, I will go into what I did with my slide presentation. Okay, so on your way into work tomorrow, a blip happens in the time-space continuum. You are transported back to the 80s, early 90s. What does this mean for your work as a software developer? Well, let's take a look. Well, I'm not sure what you guys do when you get into work, but the first thing I do is I check my voicemail, see if there's anything important, and check my email. Well, you enter your office. You don't have your cell phone anymore. Your landline, you see it connected to the wall. There's no answering phone machine on it. And you see these yellow slips of paper on your desk. Well, those yellow slips of paper were your secretary took messages for you when you were out. So in the 1980s, NCAR had a single telephone number into the organization. And you had extensions that would ring on your personal desk. And when someone called and asked for you on the NCAR line, the operators would look you up in their list and they would transfer the phone to your desk phone. If you didn't answer after 4 or 5 rings, that phone got transferred back to the operators. They would ask, do you want to leave a message? If you said yes, then they would look up who your secretary or secretaries were. Sometimes it took a couple of secretaries to get one that was at their desk. And then they would take that phone message for you. Okay, well, check your email. Well, email didn't exist. Instead, you had a physical mailbox that you would go to. And that is where you would have things called memos and other mail. And so you would walk down the hall at least several times a day because NCAR had deliveries, internal deliveries several times a day, but your secretary could leave a memo in that box any time of the day. So your daily routine was to go down there multiple times. Okay, so let's take a look at what a memo looks like. Well, it looks surprisingly, or maybe not surprisingly, like an email. It has the to, from, date. It has a subject line. It has a text. And in this particular case, some things never change. It was requesting that we manage our limited disk space. And so they wanted to notify users of being sure that you were cognizant of your usage of the data system. But there are other things on this memo that aren't in line with email. So a physical received stamp, you see that right here. Notice that this date, May 15th, is 3 days after that memo was sent on May 12th. So communication was not instantaneous by any means. Up at the top here, well, you can see this memo was sent to the NCAR directors. Well, I don't know about you, but none of the lab directors here would be in charge of, taking care of the disk space. They would be telling people, you need to take care of the disk space. So that's what this was up here. He said, please handle, and he put his initials. And so then the secretary would go and say, okay, well, I know these people are on the computer. She would go down the hall to the Xerox machine, make copies, and then put it in everybody's mailbox that was appropriate for. So copy machines were highly used. Can you imagine if this memo was to the NCAR directors and it said, everybody needs to know this because, NCAR's taking an extra holiday this year or something. The secretary would make a copy for every single mailbox. So we went through reams of paper. Well, memos were so prevalent that there were even tablets of paper dedicated to them. So in your office supply cabinet, you could get a, memo pad and leave your own memos. Well, another thing that doesn't change, cybersecurity. So if you look at this, in 1991, our sysadmin sent out a memo to everybody about a hacker, and look at this, hacker is in quotes, because at this point in 1991, hacker was a colloquial term. It was not accepted. Now, we just know a hacker, it's in the dictionary. But hacker was it was a word that was up and coming. A hacker had gotten in, had TFTP'd our password file, and he was on the NSF net. Okay, so back in 1991, with limited people, we still had hackers out there. So what was the NSF net? It was a precursor to the internet. So if you look here at this diagram, and it's in one of these books up here, the NSF net connected some of the supercomputers and universities, but you can see that dark line, that's all that was connected, just those dots on that dark line. There were other networks, there was the West Net and the Northwest Net, and they were separate. So if you wanted to talk to somebody on one of those networks, you had to, you couldn't. But as time went on, the network started getting more connected, and I'll talk about that later. Okay, well, yeah, we finally gotten through our voicemail. We finally got through our email or our memos, and now it's time to start that programming assignment. But you want to check a detail. You aren't quite sure about the specifications of something. So how do you do that? Well, Google didn't exist. So you had to rely on different sources. So first you'd go and check your bookcase. Your bookcase was full of things that you kept that were useful for you. And so you would have books that you had purchased from the bookstore. You'd have things like these quick reference guides. These were great because they were a summary. They're kind of like what a man page gives you these days. Gave you a summary of all the different things that were available. NCAR made some. You can see some of these were NCAR made, and then some of these were vendor provided. You also depended on manuals from your vendors. Craig had really cool manuals. They were in these nice silver binders and kind of glossy front page, but they had all the data that you needed to know about using the various computers. So you would depend on the vendors' manuals to give you the specifics of how to run on that computer. And then NCAR, as I mentioned, they self-published those quick help guides, but they also published books, and I've got a number of those old books up here. In this case, this was the Fortran reference manual. You didn't have a way to look up, what is that Fortran command that I forgot? You had to go find a book somewhere that gave you that information. If you notice at the top up here, J.C. Adams, that was Jean Adams. She was the lead author on this publication, and she was an NCAR employee working in the consulting office, but she was also on the standards committee. So if you ever had a Fortran question, you go hunt up Jean, and she could tell you definitively what the command was that you wanted. Mentioned the consulting group. They were fully staffed. There were a number of them available at one time because, as you can imagine, questions you couldn't find in your book, questions you couldn't find in the vendor book because you didn't know quite where to look, you would go and you would ask the consultants. If you notice on her desk here, there is a bound collection of manuals. So she had easy access to all the things that she needed to answer questions and help people out. We've got Dick Valent here. He was a member of the consulting group back in the days I'm talking about. We knew each other well. Okay, another source of information was the NCAR computing news. It came out every 2 months. It was, here's what's new with the NCAR computing system. If you look at the cover, here's some state-of-the-art graphics. This was a really cool graphic that they wanted to put on the front page. And then you could see there are 3-hole punches. I did not put those in. They were delivered that way. The intention was if you had an article that you wanted to keep reference to, you would probably put it in a 3-ring notebook. So this one I probably kept because it was talking about the new Fortran 90 use vector intrinsics and where constructs. So I probably kept that for future reference. Okay, well, if you still need help, you had other sources of information. You had your file cabinet. Remember when I said that I got hired to NCAR to help a scientist organize his journal articles? He had file cabinets full of journal articles he had Xeroxed over the years because he needed to be able to reference them, maybe even cite them in a paper. And so he put them in file cabinets. Well, you can imagine you can only do so much with your file cabinets and you tend to lose things. So that was my job, was to help him get that organized. Oops. This is really touchy. Notebooks. You would write down everything. So I have notebooks from my early days. I'd write down things every day that I wanted to keep track of. You would physically go to the library and do research there. And then you would ask colleagues. We bounced ideas off of each other all the time. And you don't realize today how much you depend on Google for that information. So you can see this evolution of storage from paper to digital by just looking in my office. So this is my office. I have 3 file cabinets. Everything in those file cabinets is older than 10 or 20 years ago. But I need to keep them because they are my only archives of some of the things that were important back then. Okay, well, now you've got your information. You are ready to start writing your program. You're getting down to it. Well, you better pull out that paper and pencil. That is how we wrote our programs. We didn't have access to word processors or digital editors. So think about that for a minute. We have cut and paste, right? Literally, back in the day, we would sometimes cut and paste because we didn't want to rewrite that stuff. Or maybe tape. I did more tape than paste. You would handwrite out every line of code, and your hand would cramp after a while. So, we kind of take our editing for granted, but it really was a more manual process. Okay, so you've got your program written. It's on a piece of paper. written in pencil, how do you get that into your NCAR computer? Well, you would do that with punch cards. So these are punch cards. I'll have them on the table up here. And so this is how the computer got that information. Okay, so let's take a look at a punch card here. So up at the top here, that is the code. Well, you'll notice this is one line of code. So you had one line of code for every punch card. So just imagine that. Well, this card has an 80 character limit. I mean, it only goes for 80 characters. In Fortran, the first 5 characters were for labels. So if you had a do loop, it would say do and go to the end of this label. And I'll show you that in a little bit. The 6th column was reserved. If any character is typed in the 6th column, this means the card is a continuation of the previous card. So basically, you had 66 to 74 characters that could be your program. The last 6 or so could be used. You didn't have to use them this way. They could be used for you to sequentially count your cards. So if you accidentally dropped your cards and they got mixed up, you could take them down to the card reader and tell it to sort them by number, and it would do that. Most of us didn't use that, because think about it for a minute. You've written your program, you've gotten it all sequential, and then you realize you've got an extra equation you want to throw in. You throw in the extra equation, and all of a sudden your cards are not numbered right. So I tended to use the full length of the card. But again, you're only limited to 74 characters. Okay, so how did you get these punches on your card? Well, down in the first basement, we had a key punch room. And you can see over here, here is a pile of unpunched cards. So you go over that pile of cards, you grab the set that you needed, you take them over to your key punch. Okay, so let's take a look at what the key punch looks like. This isn't exactly what we had, but it's very similar. So you would load your cards up, your blank cards up in the code card hopper, and you can see it looks like a typewriter. And so and it really was. It was a typewriter, and it would, every time you made a character, it would punch the appropriate slots for that character, and then you would write your program, and it would write the code across the top. And then as it proceeded, then it would stack up the cards that were finished up here. I do remember our card punch had a discard pile. So think about it for a minute. I mistyped a character. How do you undo that on a punch card? Well, you undo it by hitting the discard and starting over. So I'm not a good typist, but I became a careful typist when I was typing with the punch cards. Fun aside, I would take the discard pile home, I'd write on the back, and these would be my grocery lists. Okay, was there anything else I wanted to touch on that? Think not. Okay, so think about it for a minute. Your program, it's on these punch cards, right? You have written it, and this is where your program now resides. So you would either group them together with a rubber band, or if it was a big thing, you'd put into a box. And if you wanted to update that code, as I mentioned before, you'd go in, you'd look through your pile of cards. And if you have a big program, you've got a lot of cards to look through, kind of know where to go. And then you would physically pull out those cards that you don't want, and then find the places to put in your new cards. So you had to manually keep track of where your cards, where your program, the lines of code were in your program. Okay, your code lived in this deck of cards. It did not reside on the computer. After you gave it to the computer ran it, gave your cards back to you and your output back. This is where your program lived. So people kept their cards in their offices. So if you were working on multiple programs, you had multiple decks of cards. And if the card reader happened to scrunch one or more of your cards, which it was known to do, you had to go take your deck, go punch those cards again, find the appropriate place to put them in, and maintain it that way. Okay, you're thinking about that program you have in now time. How many boxes of cards would it take? This box here would hold about 2,000 cards. So think about that for a minute. How many lines of code do you have? Well, as I mentioned, I work on the atmosphere model known as CAM. It's roughly 1 million lines long. So at 2,000 cards per box, it would take about 500 boxes. Well, each box was 10 to 12 pounds. So that would be 2 tons that I would be taking to the computer room to run the CAM model each time. And remember, you get to haul these up and down. They don't have storage space for your program downstairs. You're taking it back to your office. Okay, your program's complete. Now you need to get your I/O in shape. Okay, so you need to get your input data. So let's get that input data into our computer. Well, you physically had to get the input data. So this is a request that I made back in 1989 to get some satellite data, the satellite data from Goddard Space Flight Center. Probably gave them a long distance phone call, said I wanted the TOMS, Grid T, and the ERB Sage 2 data. Could you please send it to me? They physically mailed me 7 or 9 track tapes for that. So I got 4 tapes, and you can see at the bottom here, it says, please duplicate and return our tapes, or give us 4 new tapes. They didn't want old tapes. They kind of caught on pretty quick that people gave them the old tape that had too many errors on it. So you either had to return the tapes they gave you or give them 4 new tapes. So we're mailing 9-track tapes back and forth. You don't get your data instantaneously doing this way. So I had made that request weeks before I wanted it. Okay, so now I've gotten my tapes. They've arrived in the mail. I need to take them downstairs. So I would take my 9-track tape. I put it on my arm. Now each of these, they're not real light. I take them down and give them to the tape librarian. She would then give me a number. She had sequential numbers printed out. She'd give me a number. It was just a random number, a V something. And then I would, in my notebook, I would write down V something or other is this tape. And so I had to keep a manual track of what my tapes were, so that when I wanted a specific tape, I could tell it what number to use. So let's take a look at this tape. Okay, 7 and 9-track tapes looked identical. You couldn't really tell the difference. The machines could, and you needed to have the right reader for it, but we could not. They're heavy. It's 2 to 3 pounds each. Okay, so when I'm taking my 4 tapes down, I've got 8 to 12 pounds on my arm. Well, sometimes I needed more tapes than that. So then it was a decision. Do I load up 2 arms and get really heavy, or do I make 2 trips? So, those were the decisions you had to make back in the day. Okay, if you look on the back side of the tape, there's this write ring. The write ring, if you wanted to write, the operators would insert the ring in, and that would allow the tape to be written to. If the ring was out, then it was physically impossible to write to the tape. So you wanted to protect your tapes, and you only gave it write permission if you knew you were writing it. These things, because a lot of times you didn't want to write, so you would pull them out. Your desk drawer had so many of these, I mean, you could take them down to the computing room, but, that's 3 floors down, so. So the tape operators, so this is back I think it was the 3360? 3600, yeah. But this shows what the tape drives look like. You can see the tape would be mounted here, and it was reel to reel, so the other side was the pickup. And so when you requested a tape, the operators would go into the tape library, and if you remember the tape library, so they'd go look through this stack of tapes that are in order, so it's easy for them to find it. They would go physically grab that tape, mount it on the machine with or without the right ring, as you specified, and they would then open up, so they take out the outer thing, and they would load the tape. Then when they were done, they would take that, they would rewind everything. Oops, wrong way. They would rewind everything, put it back onto the original tape, and then put it back into the tape library. So, as an aside, this image that AI generated for me, I'm kind of wondering what they thought the operator did. Did they stand there and hold it the whole time? I can see my fingers getting burned as that tape whipped around. Okay, so what are the specifications of a 7 to 9 track tape? I mean, this thing's huge. It must hold a lot of data, right? No. So there were different densities of tape. There are 800 BPI, 1600, and 6250. Of course, 6250 were our favorites. They held a whole 170 megabytes of data. So it took 3 to 5 minutes to read this whole thing. And then to rewind it, it wasn't a fast process either. So let's take a look at what happens when you only have limited space on your tapes. So remember, I worked with a satellite group. We were taking information from our satellite, processing it and storing it. This is how our tape data was stored, or our satellite data was stored. It was stored on tapes. So storage is a premium. You can't store a whole word. So if you take a look at this, this is our actual archival format. It was written down on a piece of paper. You had first 32-bit word, stored 4 things. You had the record ID for the first 8 bits. You had a spare in case we came up with something we hadn't thought of. We had the map type and the number of waves. So we had 4 pieces of information in that 32-byte word, or bit word. So we really, truly were bit twiddlers. So you would read these in, you had special utilities that would unpack the words and give you the variables into their individual slots. So you can see the first 9 32-bit words held 21 variables. So you really compressed, you used every bit of information. Okay, so now you're thinking about it. You've got this tape back in the 1980s, but in now time, you've got that 512 gigabyte memory stick in your pocket. So how does that compare? Well, if you were to take those tapes and stack them, they'd be as tall as the Statue of Liberty and weigh as much as an elephant. So, you know, that 512 gigabyte stick that you had in your pocket would be this size. The other thing that you don't think about, this is sequential memory. So if you want the last word on this tape, you have to spend 5 minutes reading to that position to get that last word. Whereas with the 512 gigabyte memory stick, you can get any word you want instantaneously. Okay, well, we've got our program done, we've got our data, it's now time to run our job. So how did you do that? Down in the first basement, that's where the machines lived, the operators had a desk, and you would take your card decks down. There'd be a stack or a line of cards, they'd be queued up just like people would be queued up. You'd put your stack in the end of that queue, and then the operators would process through it. Obviously, you know, you can't stand there and wait for it to be done because there's 6 jobs in front of you that have to run. So you'd come back an hour or 2 later. You were lucky to get a handful of jobs run in a day. So, you know, we depend on I'll submit this and find all my compile errors. I'm not going to think about it. But back in the day, you really thought about things because you knew you only had a few tries in a day to do things. The other thing that was a big decision, you've got a job. You really, really want to see if it's done. How many of us do that Q stat to see if our job's done? and we're doing it like every 10 minutes. Well, you physically went downstairs, and you didn't want to go downstairs too often because the operators kind of see this person coming back. So, you kind of weighed when you thought your job might be done. Okay, so once your job's done, how does it communicate to you that this is what happened? You would get a paper printout like this. Okay, so this would have, inside of it would be your program and any compiler errors that you had. If your job didn't have compiler errors, at the end it would probably have the data that you'd written out. And if you asked for the program listing, it would be in there. Well, this is actually how I archived a deck of cards that I was getting rid of. It was a program that I'd written. I didn't want to totally abandon it, so I had the computer write out my program, and I've stored this in my file cabinet to, archive my program. Okay, so let's take a look at this job. This is state-of-the-art Fortran. We were modern Fortran programmers at the time. So you'll see there's common blocks. Well, these were data that could be used by any program unit. It's kind of like module level data in modern Fortran. There were data blocks to initialize data. And you might remember I mentioned the continuation lines. So this subroutine call had too many parameters to fit in the 80 characters, so it was continued. A practice that we used but wasn't mandatory was we numbered our continuation cards so that you could see, how many continuation lines there were. But again, it wasn't necessary. All Fortran cared of, is there a character, any character in this column? And then it would say, okay, that's a continuation line. Look at how compact this is. Well, when you've got 80 characters, you're not wasting space on blank spaces. So everything, you have no blanks between the commas, you have no indentation. So looking at do loops, you can see we didn't waste space on indenting our do loops. Here's the labels I talked about. So here is the do 1999, and it goes down to this continued statement. And this do loop 1998 goes down to this continued statement. So, you can see it's kind of hard to see this stuff. But this was the constraints we were under because we only had 80 characters on our punch cards. One of the cool things that NCAR had, though, was a preprocessor called IFTRAN. And we loved IFTRAN. IFTRAN allowed a couple of things that were really special. So you can see this do loop is unnumbered. It goes down to that do loop down here. You can see that the same thing with if, else, ifs. We didn't need to have labels on them either. So it's kind of getting more towards the structured programming that we're all familiar with whatever language we're using. These cards were actually punched. So this if block here started in character 7, but because I was using IFTRAN, it would automatically indent it for me on my printout. So I could get these nice looking printouts of my program just by using IFTRAN and using the IFTRAN constructs. So your deck of cards doesn't only have your Fortran program, it has your job control language. Oh, and one thing I did want to mention back here. This program here that looks so foreign to us has all these things that we don't do anymore. Fortran still would compile that if I wanted. That's 40 plus years later. Fortran could still handle this. We recently did an upgrade on our Python, and we had to redo some of our things because Python, in the span of a few years, had deprecated and eliminated some commands that we were using. So, Fortran has, kept that legacy for us. Okay, so your card deck didn't only have your Fortran program. It also had your job control language. So you had all of that. Those were the first cards in your deck. So you would have your user number and your project number. It would, in this case, it was a printout, so it's telling me how many allocations of the GAU units I had. So that was the units that were your computer allocation. It would tell you how many you've used up at this date, so you keep a track on that. This would be where my tape would be. I'd be telling them whether I wanted it to be read or write. In this case, this was a little bit beyond that. This is on the TBM, which was a storage that we had that wasn't 9-track tapes. It was a more, they were bigger, much bigger tapes and held more information. Down here, you can see I've got my iftran command. CFT was our compiler on the Cray. And then you had to tell it to load and save your output and other things. So all your job control language was at the front of your deck of cards. And then at the very end of your printout was how many GAUs did you use? So you always checked this. This was tiny because all I was doing was printing this out. So, you know, it wasn't a big run by any means. Okay, well, now we've got our program, we've got our data, you know, that supercomputer we're running on, it must be fantastic, right? Well, as Rory said on Monday, the Cray 1A, serial number 3, it was one of the fastest, it was one of the 1 to 3 fastest supercomputers in the world at the time. It was delivered in 1977. It was active for 12 years and decommissioned in 1989. And scientists came from around the world to run their computer models on this computer. So it must be fantastic, right? It's got a whole 0.16 gigaflops. It's got a single processor and 8 megabytes of RAM. It weighed 5.5 tons, 150 kilowatt hours of power required, and cost a measly $8.8 million, which in today's money is about $47 to $48 million. Now think about that. This is the best computer in the world, and it's got a single processor with 8 megabytes of RAM. Now you can see why this tape, you had to process things as you went through, because the Cray couldn't handle reading in the whole thing at once. Okay. So you realize how good you had it yesterday. You think about that cheap watch. We're not even talking the Apple Watch. We're talking that cheap watch you bought at Target, the smart watch. It runs 5 to 50 gigaflops. It has 1 to 4 cores in it, 128 to 512 megabytes of RAM, weighs an ounce, and costs $40. Or your PlayStation 5, you know, it does 10 teraflops. It has 8 cores and 16 threads, weighs 7 pounds, consumes maybe 200 watts of power, costs $499. So it would take 30 to 300 Cray 1s to duplicate that smartwatch, and 60 to 70,000 Crays to duplicate what one PlayStation 5 is that you have, you know, just in your house. This is just 45 years later. It's amazing when you stop to think about that. Okay, so you have access to other computers as well, because we can't all run on a Cray, right? But each of those have their own proprietary operating systems. So let's take a look at that. So Cray used what they called ucar-sea. So Unix, which was the predecessor to Linux, Cray made some extensions on that. And you can see this kind of looks like Linux to us. We can probably understand most of these. So, you know, it's not too far off. But you also have access to a VAX. So the VAX has the VMS operating system. So while Fortran was standard across all computers, operating systems were not. And there was no overlap, and you'll see that when we look at the VMS operating system. Okay, so this is a cheat sheet that I had for my VMS. It shows the different commands. So if you want to do PWD, a print working directory, you would type out show space default. There were no shortcuts. You typed out that whole thing. If you wanted to get your creation date, well, directory was like ls. But if you wanted to do modifiers, so we do ls dash whatever, you would do /date /protection, and this would be how you'd get your creation date and whether it was read, write, protected. So VMS was very verbose. We all hated it. But it was what you had to use when you worked on a VAX. Okay, your job's finished. It is now time to see your results. Okay, the cool part, the graphics. Well, NCAR had their own library that they were developing, and it evolved over the years. It started out, it was known as Autograph. It was a simple black and white graphic printing, and then evolved over time and became a color. So you can see the evolution through the manuals, and I've got those up here. Okay, but your output, you don't have a computer terminal to display it on, so how did you get it? Well, you would go downstairs, you'd have a box like this. This box had your microfilm, and that was how the first graphics was output. Later, we evolved and we got microfiche. Well, we liked microfiche. You could see that storing, 10 runs of things, you're taking up a lot of disk space, whereas with 10 runs of this, it was much more compact. So we preferred these when they came out. And then as time went on, we got to the point where we started doing color, and so we would get color slides. And so the slides would be in the deck, in the box here, and we'd get boxes, and we could store them. So let's take a look at each of these. Microfilm. Microfilm was a series of just plots, and you would have them on a reel. You had to have a specialized viewer. You really can't see things on this. You could see that there's some individual plots, but you can't see anything on that. You would take that to the viewer and you'd look through your data. If you wanted to see the last plot, you had to scroll through. So you'd hit the fast forward button, you'd zip through and you'd overshoot, and then you have to go back. So it was a hunt and peck trying to find the plot you wanted to see. It was sequential, and so you just had to deal with that. Another thing that we liked about microfiche when it came out, of course, it's random. It's not sequential anymore. So if you wanted to go to this plot here, you could just kind of navigate your viewer over to it, and you could see it. So it was much easier to find the plot as well as to store it. So that's why we really liked the microfiche. And then for the color slides, this was the way you got your color output. And so you could hold this up to a light. You can kind of eyeball the plot and see what it is. The other cool thing about color slides over both microfilm and microfiche, you wanted 2 pictures, you just pulled out those 2 pictures. On microfilm, if you wanted to keep 2 pictures on this, you kept the entire reel, and you just took up your storage space on your in your bookcase with it. Okay, so to view these things, the library had special viewers. So you would take your microfilm or microfiche or your color slides down to the library, and you take a look at things. The microfilm and microfiche reader was a specialized reader. They had some that would do both. So they had, this one doesn't show it, but they had a reel on each side, and you could feed it through, or you could put the microfiche on the platform and view it that way. But if you wanted to get a printout of what you had, what would you do? Well, they had thermal printers attached to them. So you can see this is an actual output from the thermal printing. It's a piece of paper. It's kind of glossy. It's not very high quality. Things are crooked. I mean, but it is the way you would get printouts. It was heat sensitive. So this is a thermal activated paper. So if you happen to leave this on your desk had sunshine shining on it, you could get that whole thing turning black. And you can see at the top up here that this actually did get heat activated somehow. Didn't ruin the thing, but it was starting to turn. Okay, well, some of the technology changed pretty quickly in the 80s and early 90s at NCAR. So if you didn't go back quite as far as the punch cards, we had what were known as VT100 terminals. So this big terminal is just a dumb terminal. It had no processing power. It was just taking the command or the keystrokes that you typed on the typewriter and sending them to whatever computer you were hooked up to. So as NCAR got, the networks got wired in the building, the VT100 slowly replaced the punch cards and then eliminated them. They were a shared resource though. So if you, my group had, I don't know, maybe 3 or 4 VT100 terminals. And there were probably 5 or 6 of us that did programming and wanted to use them. You kind of got into work early, so you could beat out your colleagues to get one of those VT100 terminals and get your work in and submitted. Well, personal computers came along in the early 1980s, or 1990s, sorry. The first people that got them were the senior scientists because they were expensive. They were, they were an expenditure. So the senior scientists got them. But then as the prices dropped, they became more of a thing that everybody got. And it was really amazing how quickly it went from being just the few people could purchase them to everybody had one on their desk. They really became the necessity. Okay, going back to the NSF-net. Remember, I was talking about that being that separate network. Well, in the early 1990s, that was expanding too. And it was originally a government and university-only network. So you had to be in one of those entities to be a part of the NSF-net. Then in 1991, commercial traffic was allowed on it. And then in 1995, NSF-net was replaced by the commercial internet, as we kind of know it today. So that was huge. Instead of us being able to just communicate with those few select universities and other supercomputers that were on our network, now we could communicate with anybody that had an internet access. So the 90s were when there was this huge step forward in computing, the way we do computing. We got word processing and editing. No longer did you have to use that paper and pencil to write your programs and then punch them. You could now type them. You can go backspace. I can be a terrible typist again and still get my work done. Email replaced memos. Now you didn't have that 3-day latency from when the memo was written to when you got it. You had instantaneous, which might or might not be a good thing, but you had instantaneous access to memos from people. You could get internal and external communications immediately. And then you had access to all this information. No longer did you have your bookcase and your file cabinet and the consultants that were your only source of information. You now had the world at your fingertips. First with Mozilla and Firefox and eventually with Google. So personal computing evolved their data storage too. I'm sure most of us are familiar with these floppy disks that went into our Macs and things. But before that were 5 1/4 and 8-inch floppies. If you've ever wondered why this is called a floppy, it's because these were the predecessors and they were floppy. So at this point, this is how you would exchange your data for your personal computers, but the mainframes were starting to do their transmissions electronically. So instead of getting this 9-track tape in the mail, you would do your submission and get things like we do now. You would say, I want to get some data, and they would ship it to you electronically. Okay, we survived our day back using that technology from the 80s and early 90s. It's time to go home. Well, after dinner, you want to check something real quick at work, but there's some obstacles. You have a single landline into your house. If you have a teenager, good luck. Actually, my husband and I both would have some heated discussions at times about who got access to the landline and the modem first. So, it was, think about that for a minute. When we were in COVID lockdown and we were working from home, we had our spouse on their computer, we were on our computer, our kids were probably doing their stuff. We were all working. Back in the 80s, 90s, you couldn't do that because you had one access point. And that access point was not fast. It was a 300 baud modem. And to add to it, if you happen to live in Longmont, which is just maybe, 5-10 miles down the road, that was across the long distance barrier. And so if you wanted to call from Longmont into work, you paid per minute charges for that privilege. So how many of us know this sound? Yep, that's connecting your modem. And you waited for that last little connection to celebrate that you were there. Okay, well, technology, as we've acknowledged through this talk, has really changed. It changes the way we work. Thinking back to how I worked, and I didn't really realize this until I was preparing this series of talks. Things evolved and we just went with it. But if you think back to how things would be if technology had not kept pace with our computers, things would be really different. But there's still one thing that is absolutely the same. This comic has been on my bulletin board since 1998. Coding is frustrating at times. This cartoon would be the same. It probably wouldn't have this big monitor being thrown over. It'd probably have a laptop, but the sentiment is still the same. Okay, yeah, I've got some time. So let's go and, before I do that, thankfully, tomorrow the blip in the time-space continuum is gone. Everything's back to normal. But now you can really appreciate how technology has enhanced the way we do our work. And I would go as far as to say, help it to be enjoyable. Because who wants to haul, a Statue of Liberty's amount of data around when you can do a 512 gigabyte thing in your pocket? Okay, so as promised, I want to give you a little insight to how I prepared these slides using AI. So I'm going to compare NCAR's Gemini, which we have here at NCAR, with the Gemini Ultra that's available for public to purchase. Okay, so about the time I was starting to put these slides together, NCAR made an announcement. Hey, we've got this Gemini. It's fully integrated into Google. Give it a try. You sign up and give it a try. So I signed up. I said, well, sure. Why not? I'll give it a try. So I sent it my text. So this is the text minus the date, because I didn't know what the date was. And I sent that text. It was just typed in. And I said, okay, brought up Gemini. At the bottom of my slide, it said, beautify this slide, gave me a button. I hit that button, and this is the picture I got. It's like, whoa, this is really cool. I've got my title slide, and all I had to do was hit a button. But, I hadn't really finished the wording on my slide, so I changed a couple of words and said, beautify the slide again. And then when I first got this picture, it didn't have Fortran punch cards. So I said, add Fortran punch cards, and it added them into the picture. And then I didn't have a green and white printout. I said, add a computer printout. First iteration it gave me was this really bright picture of a green and white printout. And I was like, no, I told it, make it a little more antique looking. Well, each one of these iterations, it was kind of interesting. I didn't realize it at first, but by the time I got to the end, this picture was looking really derelict. It was like the AI, every time it gave it to me, it was making it look more ancient and more run down. I don't know why. So anyway, I eventually said, okay, I get it. I just won't do that. So I went back to the first picture it gave me, and I told it to do everything I had done in one fell command, and told it to remove the text because I knew I needed to edit the text later. So that's what I did for this title slide. Well, then I had this boring table. Okay, so that's what the table was when in my slide deck, I said, well, let's see what happens. I hit beautify slide, and this is what immediately popped up, that slide there. It's like, whoa, this is cool. I'm gonna make my whole talk this way. So I said, great. I hit a few more slides, and then I got a message. You have reached your 30 token limit for the month. It will reset on April 1st. I went, I've got 80 slides. How am I going to do this? I can't have just 2 or 3 really cool slides and the rest of them look like this. I mean, that's going to be really bad. So reached out to my group. We brainstormed a little bit, and they said, well, let's just go have you purchase the personal AI utility on your personal Gmail account. So that's what we did. We started with the mid-level, and it was not great. So we said, okay, we're going to spend the $125 a month. So I only didn't need it for 1 month. We'll get the ultra level. So this is the best that you can get as a person that's not in, NCAR or in the business. This particular slide here, I said, well, let's see what ultra does. I'm kind of curious. It goes, I cannot handle slides like this. So only the NCAR Gemini, which is Gemini for business, I think, could handle converting that table into something cool like this. So I felt very fortunate that I actually made that conversion before I ran out of tokens. So the other confusing part is that Gemini has the version, it's called Nano Banana. It is the same name, same version on both the NCAR and the public sites, but they do work completely differently. So this is what I got. It was an okay slide, but it wasn't what I really wanted. So then I went and asked my colleagues, hey, if I give you a slide deck, can you hit beautify slide and give me back the things? And you can see, this is from the exact same prompts, so the exact same first 2 slides, and then my word slide. This is what Ultra, which is the most expensive one you could get, gave you, and this is what NCAR's Gemini Workplace gives you. So there's definitely something better that we've got here at NCAR right now, but you're limited to 30 tries. If you remember back to my title slide where I was wasting all this time, beautifying my first slide, not knowing that I had a 30 token limit, that's where I wasted most of my tokens. So was this easy? Yes and no. I mean, I'm not an artist. So the beautification was great. I mean, that slide that has the Cray, the smartwatch, and the PlayStation, that's not even something I could have imagined. I'm not that kind of a person. So to have a slide with just me hitting the button once, that was great. Context really does matter. In the case of slides, it forgets, and it only will go back 1 or 2 slides. If you tell it to do something with a couple of slides, it's kind of outside of its wheelbox. So things that you would think would be easy weren't easy, but it was great with what it did do. But because of this, with the slides, only going back 1 or 2, I had so many slide decks open on my tabs. I had a slide deck with my title theme, so to get my cards at the end, or my slides at the end, those were, I had to have just the title slides to get that. Those green section, the section slides, the green screens, that was another slide deck. So every time I wanted to add a new one of those, I had to go find that slide deck, say, here's my text, and then I'd copy it back. And then the same thing with my antique background slides. I had to keep those in a separate deck. So I had, several decks open. And then to confuse things even more, I had my NCAR user, my personal user, and I was pointing to the same slide deck and trying not to get everything mixed up. So it was a huge time sink that way, but I learned a lot. One of the key takeaways that I found is the way the AIs were. In the NCAR one, the button at the bottom is beautify this slide. And I didn't realize it at first when I went over to my personal account, that button at the bottom had different words. It said enhance this slide. Those are two completely different things. So the beautify command would take my text. It would not modify my text. It would just make it pretty. That is the standard in the NCAR implementation. But when you go over to the personal one, if you hit enhance this slide over into the AI prompt window, it would pop up with this text immediately. Redesign this slide to most effectively communicate the content, prefer well-structured visual layouts. It would actively restructure and edit your text. So your text in the personal, by hitting the button, was changed. Most of the time it was good, but not always, as we know. But the other thing that's different is this beautify command makes an image. You can't edit the image. You can tell the prompt, you can tell it with prompts, please do this, and it will do it. But once you have that image, you can't modify anything. So that's why I had to take my text off of my title slide, because I knew that I was going to eventually lose that window, and I wanted to be able to put my text in when I got my date for when I was talking. Whereas with the enhance command, it makes a slide that's fully editable. So this is one that was produced with enhance. So I could go in here, I could click on this box, I could edit my text. But with the beautify, you can't edit the text anymore, other than telling it, please take this text out. Sometimes it would take the text out, and sometimes it would take the text out and modify things. And so I learned pretty quick that, once you had an image, you just kind of quit with that slide. So if you're making a slide deck that has scientific content, a lot of these things wouldn't work real well. This worked great for my informal talk because I don't care if it changes some of my words. I can, it's still keeping the gist of things. But if you're doing a scientific slide, and if you look back, these slides I did nothing with. Because when I said beautify this slide, it made garbage that wasn't what I wanted. If I said enhance this slide, it did things I didn't want it to do. So this is more of what I would think a traditional slide for a scientific talk would look like. So I'm not sure that these commands actually would be useful for anything maybe than your title and your thank you pages. It was a huge time sink as well. I must admit, I spent way more time on these slides than I should have, but I was exploring AI as well. So, it was justified in this case, but if I were doing this in the future, I'm not sure. I can't say that it saved me any time. Actually, I spent more time on this slide deck than I normally would have. So I think that is it. So thank you. As I said before, the slide beautification enhancements were from Gemini Nano Banana. And thanks to Jesse and Courtney for giving me their AI tokens so I could make some of my special slides after I ran out. And then to let everybody know, I've got show and tell. So during the break, feel free to come up. I've got old manuals. I'll have the 9-track tapes, the printout, the punch cards. You can take a look at everything. Please handle things. I know some of the manuals are falling apart. Please pick them up, look at them. They're not going to do any good going back on my bookshelf. Feel free to look through and see what it was like back in the old days. So thank you. And if there are any questions, I'm willing to take them at this time.
Thanks, Cheryl. Question? Yep.
Yeah, thank you. This was very interesting. I'm curious if there are ways about the old way of doing thing or technology that you think might have been superior, or some things that we've lost over the years.
Yeah. I think the biggest thing for me is thinking about what I was writing before I write it. So it's so easy, you know, I'm writing a simple program. I don't need to go out and design it. I'll just kind of sit there and type it. And so, you know, I'm much more, you know, I do things much more spontaneously. Whereas back in the day, you really thought about that program because you only got 3 or 4 chances to run it. So you made sure everything worked. And you thought out things a lot more.
Thank you. I appreciate it.
Hey, super fun as always to hear this. You talked about what modern day CAM is in numbers of boxes. What was the atmosphere model number of boxes back in the day?
I don't know that number. I should have looked that up. That would have been interesting. I guess next talk.
yeah, next time. Because you'd have to run that whole set through to actually run CAM.
Yeah.
Right?
And it's in a box. So I was thinking back to so I was on the in the satellite group at the time. So that's why I don't know how big CAM was. But in my satellite group, we had code that we kind of shared. And so we either shared the boxes, you know, whoever was going to use this subroutine would go get that box and append it to their box, or we would duplicate. And so the card punch machines had duplicate processes. So if you knew you were going to use this a lot and you didn't want to keep bothering your neighbor to get their subroutine, you would get that subroutine from them. You would take it down, get it duplicated, and then you could add it to your own box of cards. But yeah, I don't know how they did the old atmosphere model back in the day.
Yeah.
I don't know if you remember, Dick, if...
The largest that I ever saw.
Do you want to go to the mic so folks online can hear you too?
I don't really have a good answer for that, but about the largest number of boxes I ever saw for one program was like 2.5 boxes of the. I thought there were 2,500 per box. But,
could be.
But that was 2.5 boxes of what I found.
Okay.
Sometimes the operators behind the counter would they'd play funny jokes with you, like they would hold a whole box up, but it wouldn't be in the box. I mean, it would just be, you'd be looking at your card deck and going, oh my God.
Don't drop it, because it's not numbered.
Yeah. I think one thing I would say is that back in the day, you saw more what I would call gurus, or people who were really specialists. And I think with the modernization of some of the things you talked about, there was more of a democratization.
Mm-hmm.
More people knew more things, and so it would save you the humility of going to the guru and saying, please help me. So there was a lot more, I think in those days, as you talked, there was a lot more interaction with people.
Oh, yeah. Yeah. I mean, I was down in the consulting office, I don't know, every other day I felt like. And nowadays I get down there once a year maybe. So, you know, but they were much more heavily staffed in the day too. I think it was like 3 or 4 of you were available at all times, right?
I didn't remember that. As I recall, there were like 2 shifts per day and 4 hours.
Okay. But I thought there was the main consultant, and if they were busy, then there were the backup consultants you could go see if...
You could usually call somebody.
Yeah.
At first, though, it was actually volunteer. I mean, I was told specifically, you won't get credit for doing this. But it's just going to be, you know, we'd like to get this started, so let's see how it goes. And Gene Adams was just great. And I'd like to also acknowledge that back in the day, NCAR was really, I think, ahead of its time in hiring females. we had quite a number of software engineers, but then it seemed like later that thinned out, and I don't know exactly why that was. It became more male dominated, and now we're back today that I think it's more, I wouldn't say equal, but it's better.
Yeah, when I was an undergrad student, I had female mentors here at NCAR, so it was nice to know that, hey, I'm in, they're my people.
It's really nice to see NCAR evolve, and of course we hope that we're going to survive this dark time that we're in right now. So thank you.
Carol?
Yeah, thanks, Cheryl. Really appreciate the talk. So your work back in the day sounds very both physical, shared, and like community oriented. Do you miss those aspects? I imagine there's pros and cons with both of them, but kind of similar to the comments that were just made. Does it feel like absolutely night and day when you look at those two time periods?
Yeah, when I think back, I do not miss carrying armloads of tapes, and it was armloads a lot of times. I don't miss that at all because they'd leave marks for hours. So I don't miss that, but I do miss the human interaction that we tended to have more. I mean, we still get together, we still talk, we still brainstorm things, but back in the day, you really were you were talking constantly because, as Dick said, there were various gurus. People had their specialties. And so, you'd go to talk to this person about this aspect of the programs, and you talk to this person about something else. So there was more interaction because you didn't have access to things online. So I do miss that part, but it isn't, we aren't in bubbles where we're not doing, not interacting at all. So I'd say it isn't too extreme.
Yeah, I like that image that you had of people waiting in line to process their Fortran punch cards. Oh, yeah. And I'm like, oh my gosh, what were people talking about in line? That'd be so fun.
Well, you would leave your cards. So the cards were the line. I mean, it didn't take too long to put your cards on the desk, but there was a line of the punch cards. So you kind of could tell from that, well, gee, there's that 2.5 boxes in front of me. That's going to take a while, so I'll have to come back down later. And if you got friendly with the operators, you tried not to get on their bad side. There was one time, so in the printouts here, you had line feed and page feed. We're kind of familiar with that and see. One time I made the mistake of putting in a page feed instead of a line feed. I went, where is my computer printout? Because there's these bins, and then I see a box with my name on it. And I went, oh no. And I go to pick up the box, and the operator is standing there, and they practically jump over the desk. Not quite, but they go, don't do that again. My kids got a bunch of paper to color on that day because the back sides are really cool for kids. So, you tried to stay on the good side with the operators. Every once in a while, if you were desperate, you could say, can I get this prioritized? And they might slip it in front of the big job if they could see your job was little. Most of the time they didn't do that, but like anything, it was up to the discretion of the operators. So again, if you tick them off, they might see, oh, well, there's that deck again. I'll just let this other thing go in front of them. So, any other questions?
Yep. Okay, everyone. Welcome back. So we're going to go ahead and kick off our next session. And we're going to start off with Maciej, Manna and their presentation, Always Measure, Analyzing Performance of Point Particle DNS Under Two-Way Momentum Coupling.
Thank you very much. I hope you can hear me. I'm glad to be joining you remotely from Kraków in Poland. So maybe a few words of background, why I'm interested in being here, because I sort of have both legs in research and in software development, because I was for a long time, 8+ years, a software developer, mainly in C++ in the industry. But almost exactly half a year ago, I decided to take at least a break and go back to research. Joined the Institute of Meteorology and Water Management in Poland, and working towards PhD, working on the numerical simulations in atmospheric science. And also I was lucky to be with you last year there on site when my partner was presenting there. Unluckily, I did not have time there. I was still buried in my work. Did not have my presentation of my own, but I wanted, if I had a chance, and now I have time for academic pursuits, to share something with you from my previous and current research. And I want to talk about performance, software performance in general, and in scientific software. I hope I do not need to convince you that we care about performance, whether it's HPC resources, whether we want some research code to be efficient enough to run on our laptops and not those HPC resources. Maybe we are preparing some operations code for weather prediction, for example, and we have predefined slot to fit it. So I guess we all have, when it counts, performance at the back of our head. And the goal of this talk, I hope you won't need much convincing, is to show you that our intuitions about performance can be heuristics at best. They are the reality of modern software, hardware, and especially our problems that we tackle in research context are complex enough to require more than just our intuitions. And to validate any performance claims that we have to measure it. It's the mantra that I heard when I was software engineer everywhere, especially in C++ world, where software performance is important. So always measure, and I want to convince you that it is very important when it comes to performance. Briefly, the slides should be available on my GitHub, so because I was overzealous with the number of slides, so I may be rushing past some of them. So just a quick refresher, then some general notions, how this modern software and hardware may lie between our assumptions about our performance, and finally some case study from the research software I was working on, and some interesting investigation and studies, hopefully, regarding the performance. Briefly, running through performance may mean many things, usually effectively using resources available by our software, but here we will limit our scope to what is often referred to as computational performance, so time aspect, how good we use our CPU, also maybe GPU, but I won't be going into that in this talk. So, but that's another level of complexity. And also we when we talk about computational performance, we talked about throughput and latency. Throughput is more brute force, how much we can do computation in a given time, or we have certain amount of computation and how fast we can go through it. Latency is more with the stability, controlling variance. It's a quite different branch of performance analysis. I won't be going into that. And there are certain absolute measurements that we can do, but usually we care about relative execution time. We usually do some changes in our code and we measure how it affected, hopefully in a positive way, the time of our execution. We measure it in terms of speed up, percentage improvement. That I think these are quite obvious, so I won't be going into details. Maybe one note: in the world of highly parallel software, we sometimes care not only about total execution time, so how fast we get the results, but also that time scaled by the number of resources used. For example, number of nodes that we use on a supercomputer, because sometimes it is important for us to preserve, do not overuse the resources we have available. Just a side note. And I won't be dwelling on that, but also what it means. I mentioned that to validate our claims, we need proper or valid measurements. So we generally use two techniques to measure this kind of performance that work in complement to each other. So both are important. We use benchmarks. So this technique separates some important piece of code and executes it over and over to establish how fast it runs in isolation. And profiling is the other side of that. We take our code as it is, maybe not in a production environment, but we can do that as well. But in its entirety, and we check how long it runs, and also if we use some good tools, libraries, we can that use either instrumentation of functions or statistical sampling that from time to time check where the code is able to give us some information about how fast it runs, where it spends most time, so-called hotspots that we can then focus in benchmarking. But this approach of taking entire code as it is also causes some problems, because it is often not easy to separate what is the root cause of some issues that we may find. So we can see these two techniques are sort of complementary. Both have contrary cons and pros. Maybe that's enough for the quick refresher. And I start to convince you of what I'm attempting to convince you, I guess, and that's great. We often have, when we start working with our code, very simple mental model that we've got our code, maybe there is compiled version in between, and it executes logically more or less how we see it in our text editor or IDE. But in reality, especially nowadays, there are a lot of layers that sort of in a very subtle way affect how in detail our code is executed. I will mostly focus in this quick intermission on the top layer. So we've got our compilers, maybe it's JIT compilers in terms of Python Numba or Julia, maybe it's just interpreters that do a lot of optimizing for us, and it's great, but sometimes maybe surprising. And also even more the bottom two layers here, the hardware, how modern CPU works, how modern architecture works. It's not very easy to reason about, and so our intuitions maybe need a lot of big grain of salt to consider them. So speaking of compiler optimization, if you are not convinced that our compilers are amazing, I will advise you to search YouTube for the series of short videos by Matt Godbolt, Advent of Compiler Optimization. It's great. It shows in a series of short movies, very small code snippets, how amazing our compilers, in this case C++, but it would be the same for Fortran and so on. How many great things it can do with that. But it is important to present our compilers with as much information as possible. It is not always possible, but the more information compiler has at compile time. So if we have possibility to give predetermined values, array sizes, the compiler is capable of doing a lot of micro optimizations that maybe as I am older among us learned a lot to squeeze a lot of juice from our code. But it is often not necessary, but we also need to know when it is necessary, because compiler not always knows that he can do such things. Also about architecture, the more we are precise, especially in research software, when we are often using very limited hardware running in on one type of device, it is good to give a compiler a hint what he has available, what kind of instructions. If you don't know the flag for most compilers, at least from the GNU package, also Clang, the march flag that creates binary code, especially for your device, and it gives a compiler much more room for optimization. Maybe I will go through that because time flies. So another important thing is the CPU, how it works. Modern CPUs do a lot of unintuitive stuff, executing instructions in parallel, predicting branch if-else branches. There are several layers of cache that make a lot of our intuitions from last century obsolete. For the classical example is the using of in C++ it's vector, so the contiguous array that is dynamically sized and double linked lists, which are pointer linked. The second one contains a lot of indirection, random accesses, a lot of breaking cache, where when CPU imports bigger chunks of memory from the memory to cache. So it often, contrary to our asymptotic analysis, the first one is the default one to use, and unless we have good reason, it is much faster, even in situations where even only insertions and deletions are in question. So this unintuitive from theoretical point of view examples are everywhere, and I have much less time than I thought for the last part, so maybe briefly, the research software adds much more to that, because often we deal with systems that are massively parallel. The execution is distributed. We use accelerators such as GPUs and TPUs. And also we deal with physical systems that are quite often complex, and there is some emergent complexity associated with these physical systems that we do not know a priori before dealing with it and getting some results. I wanted to talk about my my project that involved two-phase flow for the atmospheric research purposes, both airflow, turbulent airflow, using a pseudospectral solver, and Lagrangian particles for the purpose of estimating the collision statistics of these particles. And speaking of their the performance, the main reason was comparison of the fluid solver between direct numerical simulations and large eddy simulations. This code uses 2D domain decomposition. I wanted to talk about it more, but I think I will skip it and go directly to the a little bit investigation done using very simple manual profiling done by using several points where timings were gathered in the logical structure of every iteration. That showed quite expected results. For example, dependency of the performance on the size of particles, because it enlarges the halo regions where the particles are exchanged. It also showed that when we use LES, the grid is much coarser, as was shown here, and then the amount of particles that remains the same. There is a lot of much more particles for every subdomain to be tackled, and it easily overpowers the entire simulation and dominates the effort, as seen here. But also one unexpected, and I think I managed to finish that thought. The unexpected discovery was that there was a correlation between execution time and the radial distribution function, which at the collision distance, which is a commonly used statistic to measure how preferentially concentrated are particles in given systems. So it showed that there is some dependency on the distribution of particles in the subdomains that wasn't previously considered, that affects the performance. And this code was extra instrumented to gather the data. And interestingly, there was a correlation between all those parameters: time spent, the standard deviation of number of particles across time domains, the maximal number of particles in subdomains at that statistical parameter of radial distribution function. Here on the plot, we see that with larger particles, the system have tendency to become anisotropic, and the particles gather, when the gravity is concerned, into vertical columns that overpower some of the subdomains with huge number of particles. And in case of this base code, there is no every other less filled subdomain has to wait for the one with the maximal number of particles. So it was a bottleneck here, and lucky find was to try to change the direction of gravity, which doesn't matter for the validity of calculations in the homogeneous turbulence. But maybe here it can be seen quite well. When the gravity is aligned with the pencils of our subdivision, the there is a clumping of the particles in this columnar structure that I mentioned, but when we change it, these columnar structures are positioned across the subdomains, and as we can see, the distribution is much more homogeneous, and as we can see here, the performance for those larger particles is even 30 or 40% better, just with changing 2 lines of code in a huge piece of code. So it was kind of lucky result of that investigation of the effects of particle distribution, and contrary to previous studies that assume that it is homogeneous, so that the direction of gravity along pencils is better to reduce number of particle transfers among subdomains. As it turns out, when we measure, it is not always the case. So that's the example of that emergent complexity that also I think is a good reason for us to measure and check our assumptions. I hope I at least a bit convince you that as with tests, we want tests to validate the correctness of our code, and when it comes to performance, we want measurements to validate our claims, whether something is faster or not. Thank you very much. And sorry for being over time.
Thanks so much, Maciej, for that talk. So in the interest of time, we're just going to move along. But their email is on the screen there if you have any questions and want to reach out.
Thank you very much again.
So our next talk will be Deepak Kumar, WRF-based high-resolution fire weather forecasting, accuracy, uncertainty, and applications.
Hi everyone, I'm Deepak Kumar. Currently I'm working as a scientist with Texas Tech University, and I'm going to present something related to fire weather modeling. So it is very less to software side, so please bear with me. So the basic reason behind this work is that we have seen during this decade there has been increase in frequency of wildfire, and the severity across different areas has also increased, and for that we need very precise and high resolution fire weather modeling system for the selected area. So mostly I will be speaking about my southern plain region of CONUS domain. And we have done fire weather modeling for grid scale of 3 kilometer, and we have tried to capture the major scale features so that we can easily forecast for the region on real-time basis. So I will be showing some of the sample result, and we have tried to improvise the boundary layer processes that is happening within the domain, and we have tried to resolve the terrain characteristic within the area, so we will be able to give the more precise and accurate forecast for that. So the basic motivation behind this work is, if you see on the left side of my slide, so there has been extreme change in the climatic disaster that has been happening across globe. And if you see the simple statistics, which says that if a person had born in 1960 and if the same person had born in 2020, so they could have experienced 3 times of the disaster event that is happening at the earlier days. And if you see the statistics for wildfire, it is almost twice. So the number of times that frequency of wildfire has almost doubled over a period of time. And similarly, if you see the lower part of the same slide, the historical probability during the 1992 and 2015 for the area of land that is being under the wildfire region is more than 100 acres. So if you see that it is western side that is being affected, and followed by the southern plain region in Florida. And if you see the wildfire potential outlook for last year, you can see that almost major part of the country is under wildfire threat zone. So this is the main thing. And another thing is it is also market driven thing, that if you see the simple market statistics, which shows that there will be a 7% increase in the weather forecast industry in coming days. Until 2029, there has been projection across the globe that almost all the part of world will have this increase in the forecast market, and that is being supported by almost all the countries and mutual cooperation policy. And there has been development in technology, use of lot of GPUs for doing the forecast and all those things. And if you see the statistics for US for 2024 based on the state, so California is one of the most affected state, that is experiences almost 8,300 wildfire event in a single year, followed by Texas. So that is the area where I'm working, and that is also experiencing almost 5,000 wildfires within just 2024. And just to give a glimpse of the statistics for the California wildfire event that occurred last year, there has been loss of almost $135 to $150 billion just for one wildfire event that happened last year. And if you see the 5-year average for the same area, you will get that within just 2024, the number of emergency response that were required is almost matching the average of 5 year. And similarly, if you see the wildfire event, it is almost matching with the average for just individual year. So in line to that, we need to first map the fire risk area, and we need to deploy this wildfire weather model, so we can understand that what is the spatial spread of the wildfire and what is the seasonality in the wildfire. So in order to do that, we are doing this real-time work modeling in our southern plain region. So for that, we are technically using core modeling of WRF system that has been developed by NCAR, and we are running those system with our T2HP system, and we are doing data assimilation, and we are plotting our result with the help of Python libraries, and we are disseminating those results to different user community, and that is being used for giving fire threat index, and those data set what we are publishing is being used by them, and they are validating our result, and they are giving any feedback and comments, so then we can improvise our results. So whole process starts with the selection of the domain, study domain, and the period of selection. So as we are working in the real time thing, so we have developed customized model for the system, which is taking care of all those things. And the simple flowchart that we are following is that we are using the data from GFS, and we are putting into WPS and WRF customized model. And after that, we are doing the analysis with the generated result, and we are publishing those results, and we are trying to make sure that whatever the code we are writing, that should be reproducible in a different other area also. And these are some of the component that is being used for this work, that works on model configuration, and we are giving the parameter on real-time basis. So we are generating fire weather output for temperature, relative humidity, wind speed, and precipitation, and using those we are generating fire risk map, and we are publishing through the dashboard. So the major concern with the data the result what we are publishing is in the terms of accuracy, because sometimes there is a influence of the topography in the result what we are generating for our area. So we are trying to localize the the result, and we are trying to improvise the result that we are generating for our area, so it can be used for different application, and that is more useful for the people from the emergency manager and weather service people. And the major complexity that comes with our data set is that we are having data from heterogeneous sources. So there is a issue with compatibility of the data set, because sometime we need to integrate those data set to our model. So it is difficult for us to integrate with our running models. So that is giving one of the major difficulty in bringing the accuracy in the system. So these are some of the result that we have generated. So in this slide, you can see that we have generated a product that red flag threat index for the southern plain region, and that is giving the real-time hourly forecast for next 60 hours. So you can see the 2 consecutive forecast hour that is for last day, and that has been run at 1800 UTC, and that was valid for 22 UTC and 23 UTC. So similar way, we are plotting all the result for all 60 hours, and these are being used by the related agency, and they are giving the validation of the result, that whether it is matching with the real-time event occurrence or not. So this is being given in a way that the color which is more toward the red is having more are the location to the more threat area. So similar way, we are also validating this result with our older models. So you can see on the left side, these were our older models that we were doing. So we are comparing our recently developed model with the old one model, and we are seeing that even though the climatology of the region have little bit changed, but still it is matching with the old results. So likewise, we are disseminating the result through the web portals. And coming to the application side, so these data set what we are generating are more useful for energy provider and grid operators, and followed by urban planners and building construction industry, because they are more prone to the threat that is being caused by these wildfire events. And the upcoming thing that we are trying to do is that we are trying to do the data assimilation with more real-time surface data set, satellite data set, and remote sensing data set. And we are trying to ingest the machine learning part to the WRF-based indices that we are generating, so we can easily predict, because if we are doing with the help of WRF system, it is taking a lot of time. So if we are including AI ML based system for this, it can be easily done once we are able to train our model in a good way. So these are some of the approaches that we are trying to follow to bring more accuracy to our result, that we are trying to check it with ECM WF dataset also. If we are using GFS system and that ERA 5 datasets combinedly together, so whether it is improving our result or not. So that also we are trying to check, and we are also trying to check with the different combination of PBL systems, and we are also trying to see with change of the fuel Marshall assimilation data that we are getting from mesonator station that is spread across the southern plain region. And coming to conclusion, that the major conclusion that I want to mention here is that the major part of the work that is being influenced with that WRF system is humidity and the wind speed that is influencing a lot of result in the region, because sometime due to sudden change of wind speed or wind gust, the climatology changes, and due to that the result is sometime erroneous and sometime it is giving biased result. And there is a non-linear error amplification due to weather indices, because sometimes the combination of different parameters to generate the indices gives a very weird kind of result, and we are trying to develop reproducible workflow so it can be easily automated in other system for other part of the region. So it can be tested for other region that the model what we have developed for our region is valid for other part of the area or not. And some of the future for the future work that is being targeted, that we are also trying to reduce the humidity bias in the model, and we are trying to check our model with multiple other reason, and we are trying to integrate with ML AI. And we are also working with operational validation of our result. We are sharing our result with different emergency manager group and NWS and NOAA people, so they can give their feedback to this thing.
Thanks so much. So we have time for questions. I'm not seeing any on the Slido. Are there any in the room?
Hi, Deepak. Good talk. I was just curious because obviously, in operations, you got to produce simulations in a current given amount of time.
Yes.
And you also mentioned the need for ensembles to get uncertainty estimates. So have you found a good balance between number of ensemble members and still keeping your operational workflow?
So we are trying to test for all the assemble members, almost 100, but it is taking a lot of compute, so we can't go for that. So we have to optimize to a level that we are able to get good amount of visual match at least between the existing models and our currently developed model. So we have condensed those to 20 or 30, depending on the compute that is available, because on we are supposed to give the prediction on real-time basis, and to run one main set of the model, it takes almost 4 hours, and within 6 hours we have to refresh the data set. So within a day we have to give 4 set of complete run. So just we are having 2 hours of extra time to check with the assemble and other these things. So that is a difficulty for us to try a lot of assemble members together.
Cool. Thank you.
Okay, looks like that's all the questions. So thanks again, Deepak. Our next speaker will be Negin Sobhani, presenting benchmarking and optimizing AI/ML workflow performance for Earth System Sciences.
Oh, thank you so much, everyone. Hello, everyone. My name is Negin Sobhani, and today I'm here to talk about benchmarking and optimizing AI/ML workflows for geoscientific applications and Earth System Sciences, and some of the lessons learned and challenges that we see in this space. I want to acknowledge all my colleagues and also colleagues across different organizations. This is a work across different organizations. So. A little bit about me, if that's interesting to you. I'm an HPC user consultant at NSF NCAR. I work in Sizzle. I work with Consulting Services Group. I joined NCAR in 2015 as an intern and then stayed around since then. So this headshot that you see that I use still in my LinkedIn is from 2015. And yeah, that's never good. So some of the themes of my presentation today, because I have too many slides, unfortunately. So the themes are GPUs are fast but expensive. Make sure that you're using them and make sure that you're utilizing them and they're not sitting idle. The second point of my talk is that the scaling AI/ML workflows is difficult and it requires a lot of skill set from HPC, software engineering, AI/ML, and also domain science. And the major bottlenecks that we see is around AI and the communication. So the typical AI/ML workflow in geosciences, we typically start from some sort of data. So the data can be in different formats. We have ZAR, NetCDF, HDF5. We have GeoTIFF. We have very GRIP or different formats. And then we pre-process, there is a certain component of pre-processing and ingestion of this data. So, for example, using X-ray, DASK, and then some sort of regrading happens. There might be some filtering that happens, and the data is pre-processed and ready for training and validation. And that steps usually happens. The arrows are actually missing in this slide, but that usually happens using the frameworks such as JAX, PyTorch. I'm not a big fan of TensorFlow, so I put it out there. And that usually results in a trained model. And then after the model is trained, the users use it in inference mode for example, like similar to how WRF, for example, simulations can be initialized from another initial condition. And the training and inference step usually happens on the GPU. So the trends that of overall like AI ML adoption in earth system sciences, first we are seeing more and more data. Every startup now collects a bunch of more data sensors. There's like more satellites that we see these days, a lot more ensemble simulations, so a lot more data. And then we are seeing larger models that are being trained. So I added some stats for some of the big models or some of the big names in essentially like AI ML for system sciences. So GraphCast, for example, had around 40 million parameters in 2023, whereas ForecastNet, for example, that came out July of 2025, had around 700 million parameters. So you can see like how the trend is like going towards more number of parameters and more complex algorithms also. The models also previously was more along just emulating parts of, like, for example, microphysics, radiation. But now we are seeing models that are emulating the whole atmosphere or the whole Earth system science, like, or the whole like Earth system model. So so bigger models. And with bigger models, the problem usually is the VRAM or the CUDA out of memory issue, and I will talk about that next. So typically what happens is that training AI/ML is like going slowly, so you increase your batch sizes to make it faster, and you want also to add more layers so that you can capture more complexity around like high resolution complexities, but that results in the CUDA out of memory. I hate that error. I genuinely hate that error. So to better understand that error, we need to think about what goes on to the GPU memory. So during the training step, the model parameters, the gradients, the optimizer state, and the activations that are needed for calculating during the backprop, those go into the GPU memory. So the bigger the model, essentially, the more memory it will use, but also the bigger the batches, the more like input, essentially, parameters that you have that will go to your GPU memory. And then I added just an image of a fancy A100 here with like some of the numbers around the VRAMs. I personally have a PC that has a 4070, so that's like around 12 gigabyte of VRAM, which is decent, I think, for personal stuff. But at NCAR, we have two big machines. So we have Derecho. Derecho has a bunch of A100s, 40 gigs. On each node, there are 4 A100s. On each GPU node, there are 4 A100s, 40 gigs. We have 82 nodes, if I'm not wrong, which, do the math. 82 multiplied by 4. And then we have Casper, and Casper doesn't have a nice banner, so I tried to create a banner for it, but you can see it inside the machine. And Casper it's a heterogeneous machine. It has a bunch of different GPUs. It has like L40s, A100s, H100s, and can be used for inference and training. So two big important concepts. So first is data parallelism. In distributed training, there are two different concepts that you need to know about. So data parallelism is when your data doesn't fit into your VRAM, and then you like chunk or split your data and send it to the different workers, the different GPUs. That's like the data parallel workflow. When your model state doesn't fit into the memory of the GPU, you use model parallelism. And you split up your model and send the different model states to different workers. And then you can do hybrid parallelism, which is a combination of both data parallelism, when you shard your model and when you like split your data and send it to different GPUs. And yeah, just a quick refresher around the basic training loop. So we have the forward pass, loss calculation, the backward pass, where you compute essentially the gradients, and then the optimizer state. And the reason that I went through this step, it becomes clear for the next slide, which is distributed data parallel. So distributed data parallel is when you copy the entire model state on each GPU, but your data, you split it up and send it to different GPUs. So your data is split up, but your model states, you have a copy of the model state on each GPU. And each GPU gets, so this figure essentially explains it very well. It uses LLMs. You're not technically in like this is not an LLM. Imagine this would be an AI model for Earth System Sciences. But you can see like the data is like essentially split up and sent to the different GPUs, and then the forward pass happens. There needs to be a synchronization step, because if there isn't any synchronization step, it's as if that we are training 4 different models on 4 different GPUs if we don't do essentially a synchronization and I'll reduce the step. And this synchronization step typically becomes the bottleneck in, or this like communication step typically becomes a bottleneck if you're not careful about it. DDP is very simple to implement. There are 5 steps to implement DDP. It's very, very simple to implement, and it's very scalable. But the problem with that is that it has high memory usage. So if you are using very complex models, you need to think about how to split up your model state and send it to different GPUs. Yeah, and ForecastNet, the second version of ForecastNet was trained with DDP. So another parallelization technique is fully sharded data parallel. So this is a hybrid because you are chunking now both the model state and your data and send it to the different GPUs. And you can see that it needs now a lot more communication. So it needs to make sure that you are essentially like communicating between all the different workers. But this will let you train bigger models. So this will train, so if you have like essentially like a smaller GPU VRAM, for example, with the ratio we have the 40 gigs, or if you want to train more like number of parameters, then you need to go about like FSDP or other parallelization techniques that I have worked on developing as a guidebook around it. So this is just some documentations around single GPU training and the different parallelization techniques that exist. So we talked about DDP and FSDP today, but there are a lot more: tensor parallel, pipeline parallel, sequence parallel, domain parallel, and I'm not going to go through all of them, but there are a lot more, and they are used for different purposes. So feel free to check that one out. But yeah, so what happens typically is that we have a user that comes to us, scientists, and they have a workflow that's not going as fast as they want. And usually, especially if I explain everything well enough since the start of this talk, you'll know that like the data loading and the synchronization, these two are typically the bottlenecks. So these are the areas that we typically look at. And this comes from mostly a lot of experience with user workflows and a lot of like profiling user workflows. So this is a makeshift timeline of the host and device. I wanted to actually add an Insight Systems screenshot here, but I thought it would be easier if I make it myself and to explain everything. So yeah, so this timeline essentially shows the single GPU training and how like the different the different steps happening. So we have the host or the CPU and the device, the GPU, and typically like for example, like the batch 1 reading happens and then the batch 1 training after the data is moved to the GPU. And you can see there are like portions here, like, I don't know if this thing works. No. But you can see there are portions that where the GPU is essentially being idle, and we don't want that. We want high GPU utilization. We want to see the GPUs are saturated. So this is not a good, essentially, timeline. If I profile an application and I see this would not be good. Similarly, for multi-GPU training workflows, same thing. But also we see a syncing step, as I explained like earlier. There usually is a syncing step with the different parallelization techniques. And that syncing steps, you can definitely see the overhead of that if you profile the application. So and also like we don't want to see that as well, because that will result in your GPUs just like remaining idle and not being used much. Okay, so here are some tips and tricks around like optimizing these 2 major bottlenecks that we see. So the first one about I/O, this is actually the biggest one that we see, and a simple trick, which is very, very helpful for many workflows, is just optimizing the chunking of your workflow and also compression. But the chunking especially is very important. So the chunking, you want it to match your data access pattern. So if you are loading, for example, like all variables every time step, then you need to chunk your data in a way that you are not loading any excessive like data essentially from disk. And make sure that, just making sure that the chunking match your access pattern to reduce the unnecessary reads. And here, for example, is a result from like a real workflow. I have added the links to the example code, and there are multiple different repos in this talk I linked, so please feel free to check them out. But here you can see how with the baseline, which was not optimized for the access pattern, the throughput of the whole workflow is much slower. And this was a random example because benchmarks can be designed in a way to have a poor performance, but this was just like randomly we saw that. And this was error 5 actually, that was not chunked in a correct way. And then you can also see the compressions benefit as well. So typically, if you do not saturate your I/O disk bandwidth, then compression will be an additional overhead. So you can see with 1 GPU, but when you are going to the like higher number of GPUs, then you can see that the compression becomes important. PyTorch data loader itself has a bunch of knobs for optimizing performance. So there is the number of workers that's the number of sub-processes that can be used for data loading. If you set your number of workers to 0, this would be serial data loading. So your GPUs will always wait for the CPU to load the data, and this result in a lot of like idle time for your GPUs. Typically, I recommend people to start from 4 multiplied by number of GPUs for the number of workers. There's also the option of prefetch factor, which is the number of batches loaded in advance for each worker. There is the pin memory, so that would pins the CUDA memory to allow faster transfer between the CPU, GPU, and then the persistent workers as well. I recommend people to always, I think the default for it is true. I've seen some people using false, and then this will like essentially respawn new workers every time, which will add a lot of like overhead to the whole workflow. Again, a good reference, Earthmover has a really good blog post about this, and I've added my benchmarking code here as well. There are some also pro tips that you can do for improving and making your I/O really fast as well. So for example, with a typical workflow, there is this, again, CPU, like loading everything to CPU that happens. So with ZAR, everything is like first with ZAR and X-array, when you read the data, everything is like first like loaded to CPU, and then it has to transfer over the PCIe switch and to the GPUs. So if you, for example, like load the data directly to the GPU, that would be much faster. ZAR v3 has GPU native, fully GPU native support. There is one component of it that's not yet implemented, and that's the decompression. And there is a pull request for that that's waiting for it getting approved. But yeah, so if you use MVComp for decompression, for the GPU-based decompression, we have seen that around 30% improvement around throughput with just like GPU-based decompression in the ZAR, the GPU native ZAR. Another pro tip is using NVIDIA DALI, which moved the pre-processing essentially to GPU completely. NVIDIA DALI implementation requires a little bit more work, so it's not as easy as the PyTorch data loader knobs. So yeah, I'm not going to go over it in this talk, but I've added an example code that we have implemented, NVIDIA DALI, and how it improved the performance. And this is for an example workflow that we achieved around 17x just increase in just training throughput for a single GPU optimization. I have a better example for this. I've got a 51x increase in speed up with another example, but I should update this slide. But my takeaway was that always profile your code, and NVIDIA Insight for me is usually like really powerful, but I also get a lot more information that I want. So adding MVTX markers usually is very, very helpful. I'm not good at adding MVTX markers, but yeah, it helps a lot. Jian Sun knows. So, and then the second bottleneck is the communication. So torch distributed, and again, everything is in the guidebook that I shared the link for earlier. Everything about the communication backends and all this information is in there as well. But yeah, the torch distributed support 3 different built-in backends: Glue for CPU-based, essentially communication, MPI, which is quite good, and if you use CUDA-aware MPI, it supports both CPU and GPU communication, and Nickel, which is NVIDIA Collective Communication Library, which is the NVIDIA's GPU optimized communication library, and it's much faster, and it's recommended to use Nickel for your distributed training workflow to get that blazing fast training speed. And you can see this is from Insight System screenshot. You can see how Nickel is just like becoming an issue essentially in the timeline. The problem with Nickel is that it doesn't auto-detect the HPC network, and under HO we have the slingshot, and it doesn't auto-detect it, and without the correct configuration, it will fall on the slow socket communication, the Glue backend, and it will be very slow. So the AWS O-Fi Nickel plugin is a communication plugin that enables the Nickel to be built or to use it's essentially a translation layer between Nickel and Slingshot or AWS Elastic Fabric Adapter. But yeah, using AWS O-Fi plugin, that would make things much more performant. I am not going to talk about much about this slide. I just want to show you the results at that, how much more optimized than using the Nickel with like correct optimization parameters is. And this is log scale. So you can see, for example, for our reduce step, which was like I showed, it was one of the bottlenecks in the workflow, how much faster the Nickel, essentially the optimized Nickel is for that communication. And this is with just like a full end-to-end workflow. You can see how much, again, faster the Nickel is. and how poor the performance of the socket or the glue backend is. So I typically actually tell users to, when in doubt, using MPI is safer than using a misconfigured nickel, because when nickel fails, it doesn't like give, unless you check the debug and like have the debugging options set correctly to just like being very verbose, it doesn't give you that much heads up around like, okay, so your training is slow because of this. And then another important thing is choosing the parallelization strategy wisely. So I talked about DDP and FSDP, but there are many different parallelization. I showed that guidebook. There are many different parallelization strategies that are available out there. The easiest one to implement is DDP, and I always recommend people to start from DDP, and if they cannot train their model with DDP, then go to another parallelization. And the reason for that is that each layer of like just complexity adds more communication tags to your whole workflow. So for example, we have tensor parallel, which is great for training very big models when you have like very big neural networks, but the all reduce happens per layer, which would be a lot more communication. So we typically I typically recommend tensor parallel not to be used beyond one node. So on one node, when you have NVLink, which is like much faster, using tensor parallel makes sense because it's very communication bound, but like going beyond that, then using DDP or FSDP makes more sense. So there are a lot of like nuance in selecting the correct parallelization strategy for your whole workflow and making sure it is optimized. So yeah, so this was a too long of a talk. So if you did not listen to any part of it, just make sure my takeaway for you all is that always profile your workflow and make sure at least use NVIDIA SMI to like just check to see if your GPUs are being used, all 4 of them, for example, on the ratio. And then if you probably see like some sort of like IO bottleneck in your workflow, there are different ways to optimize the IO bottleneck, and also make sure your communication is set up correctly to use nickel with Slingshot. And yeah, so scaling AI ML, similar to scaling any the numerical weather prediction models, is difficult, and it requires all the different skill sets coming together and collaborate with each other. So yeah. If you have any questions, I'd be happy to answer them. And yeah, so thank you so much.
Okay, so I think we could do one quick question, or if there are longer form questions, we should save them for further discussion. Okay, so we'll move along. Thanks again, Negin.
Absolutely.
Okay, so our next presentation will be Jian Sun, status update of the StormSPEED project.
Okay, can you hear me? That's good. Yeah, so good morning, everyone. I'm Jian from the ACS group of CISO at NCAR. Today, I'm going to give an update about the status of the StormSPEED project. So as you can see, there's a long list of the presentations. So it's a really collaborative work. We can never make it without those guys' help. So let me go to the next slide. Great. So the StormSPEED is short for the Storm Resolving Spectral Element Dicor project. It is an NS-funded 3-year project. We have a very nice web page listed here and a very cute icon that I put on the slides. It's a cross-lab collaborations between the CGD CISO lab at NCAR, as well as University of Michigan, Texas A&M University, as well as the Sandia National Lab from DOE. So the main goal of this project is that we want to integrate DOE's COCOS Dicor into our CAM community model, short for CAM. And it is a special element-based Dicor, but it is for non-hydrostat simulation. So we short it as SENH in the following presentation. So the focus of this talk will be breaking into 4 major parts. First, I will briefly describe how we integrate that COCOS die-call into our CAM framework, which is mainly like Fortran-based code. And then we're going to evaluate the performance of the SENH die-call on different resolutions, as well as different GPU architectures that we have at NCAR. And last, we are going to mention that how we develop an automation of the continuous integration test workflow on NCAR's on-prem cloud server and how it helps our software development cycle. So first part, how we migrate the SENH die-call into CAM. So to do so, first we need to get the source code of the COCOS die-call from DOE, as well as our own CAM's Fortran code here, natural, and then to address the language interoperabilities, we need to develop a shim layer so that our Fortran CAM code can call the COCOS code, and the COCOS code can pass the data back to the CAM Fortran code. So fortunately, DOE does it for us automatically. So the major part of this project falls mainly on how we update our CAM infrastructure to recognize the SENH die-call. So this include, but not limited to, first, we add a Git submodules for both the COCOS library as well as the SENH die-call, so we can update the version quite easily. Second, CAM naturally doesn't use COCOS, so we have a choice. Should we just build the COCOS as a system module, so you just load it as needed, or you want to build it from source like other libraries we have in CAM, so user can configure it. So we end up with adding both options into our workflow, so user gets the full flexibility, whatever they prefer. And also for the COCOS die-call, DOE has switched fully to a CMake-based configurations, but our CAM model still use like a Makefile classic file system. So we need to figure out a way how we make the Make system as well as the CMake system talk to each other. We are not missing any options or compiler flags. And also, although I said that the SENH die-call is a special element-based method, they do change their interface a little bit. They change some variable calculations. So we need to make sure that the process interface and the variable mapping are done correctly before we create some garbage results in the simulation. But once we got everything done there, we also need to define that what test we should do for the SENH die-call in the CAM framework so that we can check that we are doing the correct things to return the correct answers. So that's basically something we need to answer. And once we get everything done, then we start to do some testing to see what the new die-call performs in CAM. So the machine we use for the testing here is our supercomputer at NCAR. It's called Rachel, everybody knows. It's a heterogeneous machine that we have the AMD Milan CPU nodes as well as the NVIDIA A100 GPU nodes there. And also I said I'm going to test how the COCOS die-call can run on different GPUs. To do so, we also use our Casper supercomputer at NWC. So it has like A100 GPUs, H100 GPUs, and recently they add AMD MI300 APUs there. So I'm going to show that whether COCOS can run relatively easily on those different GPUs and how it performs. So to show the performance, first we look at the strong scaling of the SENH die-call in CAM. So we only work on die-call, so in all the tests here, I explicitly turn off the physics calculations. I turn off the history I/O output, so the only thing here matters is the die-call computation as well as the communication. So as I said in the very early slides, we are going to test the performance on various resolutions, see if the code scales, if it matters for the performance. So we begin with the coarse resolution simulation, which is typically we do at NCAR is like a 1 degree simulation, relatively about 100 kilometers. And then we move on to a high resolution, which is like 7 kilometers globally. For this one, we can run both CPU and GPU runs. And then we move on to something we call the ultra high resolution, that is 3.5 kilometer. For these resolutions, I can only show the result on the ratio on CPU because it doesn't fit the GPU memory, so it will just blow up, unfortunately. But yeah, we will see how it works. So here's the strong scaling results for the 100 kilometer simulation on the ratio for the SENH die-call. So it is log scale. The y-axis is the maximum work clock time per time step, and the x-axis is number of compute nodes. So the lower value, the better performance. So the red line is the CPU scaling results using a full CPU node. It generally scales relatively linear if you compare with the dashed line, that is the reference for the linear scaling. And the GPU simulation result is the green lines. You can see it shows benefit compared with CPU only when you scale from 1 node to 8 node, and it starts to run even slower. And also it doesn't scale very well. You can see it lost scalability really quickly after you are using more than 2 nodes, and that's usually expected because for the 1 degree resolutions, you don't have enough computation to saturate your GPUs. So typically you have very low computational burden on each GPU. That's why you lose the scalability. But we can also plot the computational time on GPU only. That is the purple line here. Again, it lost the scalability, which confirms our assumption here that it doesn't have enough work to do. But if you look at the computational time only for the purple line, it's always faster compared with the red line. So basically it tells us that if there's a way that we can get rid of the communication between CPU and GPU or the data transfer, we can benefit from GPU even if we are doing 1 degree simulations. But this plot also tells us that there's a huge gap between the green line and the purple line, that is data transfer. And it tells us that for this particular test, we are spending most of time doing just CPU to GPU data transfer rather than doing the computation only on the GPU's end. That's for the 1 degree simulation. And now I said that we want to test the performance on various GPU. So I also run the 100 kilometer simulation on Casper with different GPU results. So there's 3 bars here. It is A100 GPU, H100 GPU, and MI300 APUs. The green bar is the total computational time on Casper. And I want to mention that to perform these simulations, I just need to change the backend of the Cocos library. There's no single line change of the source code, which I think is really nice. I don't get any complaint about compiler or anything like that, so it's great. But if you look at the green bar, the result doesn't really make too much sense. Like first it tells you H100 GPU is even slower than APUs. I think nobody believes this result. NVIDIA would be crazy saying that, really, I'm doing the right things? And also the MI300 APUs, you would expect, wait, like this is like a very advanced architecture. It just gives you less than 2 times speed up. Are you crazy? So I further plot the computational time only on GPU. And this time, I think it looks more reasonable. It shows like the purple bar here. So basically you see the H100 GPUs, it gives about 2 times speed up compared with the A100 GPU node. That is more expected based on their GPU configurations. So it tells us that, okay, H100 GPU does run faster on 800 GPU for the computational part, but why it is slower on the overall performance? It spends more time on the data transfer, and it turns out that Casper has a PCIe topology issue for the H100 GPU, unfortunately. So it's not doing data transfer very efficiently in these cases. So that's why it's not doing correct. And for the MI300 APUs, you can see there's a huge difference between the overall time as well as the time without the data transfer. So you will say, wait, MI300 APU has unified memory. Why you still spend so much time on the data transfer here? It turns out that the DOE SE NH core, when they implement the code, they always assume the CPU and the GPU has separate data memory space. So they will trigger data transfer regardless if you are using unified memory or not. So that's what I mean, that it's not leveraging the unified memory yet. And right before this week, I have a pull request to fix this issue. So now if you rerun the MI300 APUs, the green bar will be very close to the purple bar here for MI300 only. And then you will see a huge difference between the MI300 APU compared with other NVIDIA GPU here. So that's nice. So now we look at the performance on the 100 kilometers. So we move on to the 7 kilometers for the high resolution simulation. The red line is the CPU results again on the reach, and you can see because right now we have a lot of work to do for the 7 kilometer simulations. It can saturate the GPU also well, so the scaling is way much better. It's almost linear, nearly linear in this case, and scale up to 256 nodes before it starts to deviate. And for the GPU scaling, the green line is the overall time. And now, instead of losing the scalability very quickly at 100 kilometer simulation, the GPU even scale very well. It tells you that, okay, for these resolutions, you can saturate the GPU correctly. And that's why you can get very good scaling results compared with the low resolution simulation, and give you like 3.5 speed up, even if you include data transfer compared with the CPU results. And if we plot the GPU computational time only as the purple line, it also scales near linearly, and the speed up can increase to like 7 times speed up. That just basically tells us if you want to see benefit from GPU, you do need to have a big problem that to saturate it first. And this is the result that we move on to the NE1024, that is 3.5 kilometer resolution on Doricho. Like I said, it doesn't fit the GPU memory on Doricho, so I can only show you the CPU result. But you can see when you do that, it scales even linearly on Doricho, and it scales up to 1024 computer nodes. It's almost half of the Doricho machine capacities. I try to scale the full machine, but I don't think Ben allows me to do that anyway. So I would say I stop here, but I don't think the scaling will stop here. So this basically tells you this die core really scales well. And I think that's consistent with DOE's finding on their machine as well. So that's all things about the computational performance and scaling results. Another part that I mentioned in my introduction slides that we see some challenge during the software development cycle of this project. That basically means that when the project kicks off, a lot of people will contribute to this work. We have a very active development for different features. And that's to say, we see it's very easy to introduce some bugs, or people A's change will break people B's workflow, and then we need to resolve the conflicts. And many people here works on CAM or CESM, you know that it's a very large code base. That typically means that if you want to verify your code, you probably need to have a very large set of verification tests. And typically it takes a long time to compile it. And usually I know AMP group do it manually. It probably take 1 day to go over everything. And the major thing the most frustrating thing I see during the process is that, what if I just have a typo in my code? It takes Jesse 1 day to figure out and send back to my email. I fix the typo and take another day to fix it, which doesn't really make sense. And also sometimes we know that we want to test different compiler support. We know that there's some new MPI library which may have some new features we want to test. But typically, if you want to do on Doricho, you need to submit a ticket, and the CSG group will kindly install it for you. But you know that they all work very hard on thousands of tickets. They may not get back to you very quickly, and then you just need to wait. And in many cases, my feeling is that those things are really just for your test purpose. Like you want to test if this compiler release fix a bug, or if that MPI library improve the performance, and if it doesn't, you probably don't want to go through the real production software stack on Doricho. So how are we going to address those challenges? So there are multiple solutions, but we figure out a really nice way with the CISO cloud teams that we can actually run a continuous integration test on CISO's on-prem cloud service, which is called Series. So they provide both the CPU and the GPU resources for us. So it just makes sure that you can test both of your code. Okay, here we go. So give you a CPU and a GPU resources so that you can make sure that your code is tested on different platforms. A very nice thing is that they can integrate with the GitHub Actions, because all of our code are on GitHub. So if you work with GitHub Actions directly, it's really nice. You don't need to have a separate platform to trigger the workflow. And also it works with the container technologies. What it means that the user has the full flexibility to decide which operation system you are going to test, what software stack like compiler, MPI, CUDA library, NetCDF version you want to play with, without asking any admin to do it for you. So user has the flexibility to do it. And a very nice thing, although Kevin sitting there doesn't want me to shout out, is that we have access to the GLADE file system. And everybody knows here that CAM or CSM run, they have a lot of input requirements. You probably don't want to download those files every time you trigger a workflow. So having access to GLADE just make sure that you can just run your code really quickly once it compiles successfully. So that's a very nice thing. And during this process, we asked a lot of questions. Are we doing the right things? Is there something that are missing from our workflow? The thing on top of our head is that how we handle the security. And a very easy example here is that what if you get a pull request from external unknown user saying that echo all your GitHub secrets? If all your CI workflow just run automatically, you just basically review all your NCAR username, your keywords, the series keyword, everything, and you don't want that happen at all, or at any moment. So to handle that, there are 2 layers of protection. So first, the series has a secret managers that save all the user information anonymously, which means that even if you echo the secret.username, it won't print out Jian Sun. It will print something that doesn't make sense. So that is good. And also the second thing is that GitHub has a few mechanisms that it allows the CI to run some platform only if you get an admin approval. So in that case, if you get an unknown user issue a pull request, it won't trigger the CI unless I review the pull request, thinking it is safe to move on, then I can trigger it. So it is more safe to do in that way. So here's just an example of the YAML file for the CI workflow. I'm sure most of people here knows that. So the most important change here is that instead of using the default Ubuntu or Mac OS latest runner that I highlight in the red rectangular here, you will need to replace it with a specific name that Kevin created for you as the series runner. And once you get it done, you will see on something on the right, it will just trigger all the CI workflow you define with different image you have on both the CPU and GPU on series, and you can easily catch the issues. You can see all the runs just finish within half an hour. So it's pretty efficient. So that goes to the conclusion of my talk. So in this presentation, I shows how we integrate the DOE's SENH DICOR into our CAM framework. It is a Cocos-based framework that achieves really reasonable, strong scaling results on various resolutions, and is also portable for different CPU and GPU platforms with very minimum efforts. It supports the major compilers that we test, Intel, GNU, and NVIDIA compilers, they all works. And it's also covered by the CI test that we show, which allows you to detect any code bugs at very early stage. So in the future works, because we have the SENH DICOR, it supports non-hydrated simulations. We are doing some new scientific simulations by the university collaborators at high resolutions, try to see how we can enable CAM's scientific capacity with this DICOR. And also because the Cocos is a performance portable framework, I think introducing this DICOR into CAM also advanced CAM's readiness for the next generation modern architectures. So we put the GitHub link here. Feel free to check out and let me know if you have any questions for this code base. And this is just acknowledgement for the funding support for the NSF as well as the computing support from NWSC for this work. This is some reference about the DICOR I referred in this talk. And with that, I will say thank you, and I'm happy to take any questions if there are time left.
So once again, we are a little bit behind time, but we could take one quick question if there are any in the room.
Hey, Jian, I probably should have asked you this like 2 years ago, but with your runs, like what kind of physics are you just running with? Really idealized physics? Because I know the physics in CAM isn't fully GPU enabled, so I just didn't know if that was like a drag on the numbers or if this is all just kind of DICOR is doing most of the work.
This is the dry DICOR run for all the simulations there. Yeah, so there are basically no any physics.
Okay, cool.
Yeah.
Awesome, thanks.
No problem. Thank you.
Thanks again. Excellent presentation. So now we're at the last presentation of the session, and this is Ren Stengel, evaluating the feasibility of language interoperability for atmospheric modeling using CAM parameterizations in E3SM.
Okay, hi, I'm Ren. I'm a postdoc in CISL. I'm going on about 6 months. So going into this, you should assume I know actually nothing about atmospheric dynamics, but today we're talking about evaluating the feasibility of language interoperability for atmospheric modeling by integrating CAM parameterizations into E3SM. So a lot of the motivation behind this work is that so far there's been many ongoing and past projects that involve code modernization. So we have CCPP, which provides the interoperable physics for things written in Fortran. We've had Earthworks, which focuses on GPU enablement through OpenACC directives. StormSPEED, which we just heard about, integrates performance portable COCOS for the dynamical core into CAM. And then we've also seen a lot of people starting to experiment with JAX for automatic differentiation. A lot of these efforts have different goals. So sometimes they're focused on complexity containment, other times it's physics package portability, or sometimes GPU enablement. Some notable observations that we've had as a group is that primary industry support is focused around Python and C++, and we're seeing significantly less support for Fortran, and notably less support for Fortran on GPUs, which is kind of a bummer as we continue to trend more and more towards heavily utilizing GPUs. Also, graduate students and postdocs, including myself, aren't really necessarily skilled in Fortran. And so a lot of our future scientific leaders are learning Python and some of these newer codes. And so for this project, we're kind of focusing on how does multi-language support impact community contribution for atmospheric dynamics. And so again, we've had StormSPEED, which puts the C++ dynamical core in a Fortran application. And then this project, you can think of it as sort of the opposite of that, where we're now pulling Fortran physics from CAM into COCOS, into a COCOS C++ application. And so to do that, we're using the Energy Exascale Earth System Model, or E3SM. And so that's DOE's Earth System Modeling Framework. And the main goal of that framework is to provide an Earth System model framework capable for exascale simulations. And so we're focusing on the atmospheric component, which is EMXX, and it, by kind of default, supports language interoperability for parameterizations and physics packages. And so they offer support for Python bridges and Fortran bridges, which is nice. And it's built on top of COCOS, so it does also provide hardware portability and performance, like what Jen just talked about. And so we can run it on GPUs sort of right out of the box, which is nice. They also do provide a lot of built-in like performance metrics and quite a few customizable like logging things, which are just nice for sanity checks and performance profiling. And so as far as interacting with E3SM, I'm going to go through this really fast, but they use the kind of standard .xml change functionality that probably most of you are familiar with to change comset and grid, compilers, machine environment, all that jazz, runtime and time stepping. And then they also have an additional atmospheric change package that allows you to change the atmospheric process settings sort of quote unquote on the fly. And so sort of a comparable version of that is the CCPP approach used by CAMSEMA, which uses XML files to define your run flow into a driver. And so this atmospheric change package kind of works like this, of where it sits in between the configuration phase and the runtime configuration. And so we can just in our like driver scripts or definition scripts change the processes, for example, that we would want to run. So in this hypothetical case that I don't think is something anyone would actually want to run, we can just say we run shock P3 and then MAM4, and then maybe at a different time I can just decide, oh, I want to run shock Kessler and then MAM4. So that's really nice, and then we can also use it to change our logging settings, our topography files, initial conditions, et cetera, et cetera. And so EMXX also provides some sort of under-the-hood automation for us, which is really handy. So I don't have to deal with grid management or time stepping. It takes care of that for me. It also provides pre- and post-condition checks for all fields that we're using. And so by default, it will check for any NANs, and it will throw an error if you encounter that. And so that's helpful for debugging physics processes and whatnot. You can also set custom ones saying like, I really want to make sure this field is within this range, and if it's not, then you should yell at me. And it also handles like file IO for you and field management between processes. So it's actually really easy to integrate into. In short, this is really all you need to create a parameterization. So you just need a constructor that doesn't necessarily have to have anything in it. You need to define your fields and your grid layout with a setGrids function. You need to initialize things, and so that's where you would create field checks, initialize anything that you need to, And then you have a run function that runs the physics you care about, and then there's a finalize that just does cleanup if you need to, but it handles that for you if you don't want to add anything. And so sort of phase one of this project was just creating like a very, very basic parameterization that just does an identity transform. And I was told that I had to name it after myself. So that's why that looks like that. But basically all we're doing is we're scaling pressure and temperature value by 2 and then dividing it by 2 and then returning it back. So nothing should change. It's not very exciting. And then we use this identity transform to play with these different bridge code options. And so I've built one that has, it's entirely C++ and Cocos. And then we have a Python version, which is shown in green. So it bridges to some Python code. And then we have some different Fortran versions where one is just standard CPU Fortran, and then we have an OpenACC version of Fortran as well. And so for the C++ interface, it's pretty straightforward. Basically, you just say, I want the physics grid, and I'm going to be using the temperature and pressure variables from that. We don't have to do anything for initializing, and then for the run, I'm just grabbing those fields again and doing the scaling. So it's very straightforward for this process. For Python, it's a little bit less straightforward, but basically we're just using like PyModule to call some Python defined functions. So our grid actually looks, our setGrids function looks exactly the same as it did before. And then for our initialization, we're not actually doing anything, but I'm calling an init function just for fun. And then for our main, we're using the Python version of getting fields, passing that to the Python, doing the scaling, and then passing it back, basically. Fortran, again, does get a little bit more chaotic in the sense that we found it easiest to make like a bridge layer for C++. And so sort of the middle blue box is still C++ code, but that just is acting as like a bridging layer to then call the Fortran code. And one thing to note that I'm not really showing here, but we do have to do data transposes in the middle here. And so that happens in that middle blue box before we call Fortran. But overall, it's like not super crazy in order to set up these bridges. And so sort of a few things to note, right, that I just mentioned. C++ and Fortran have different data layouts, so that we have to do a transpose on all of the fields going to and from Fortran. And so we followed suit with some of the other parameterizations in Emacs that do that, and we've been using structs to just keep track of both versions so that we're not accidentally losing them somewhere. We have been able to add OpenACC support, which none of the other parameterizations currently do that. And so it's been really cool to be able to run the Fortran bridge entirely on GPU and not have to transfer data back and forth between the CPU. And one thing that's really nice is that we can bridge directly into existing code from other repositories. So I'll talk about this more in a minute with the next one, but sort of a longer term goal is to add like a larger, more interesting parameterization and physics package into this workflow. And so phase one of that has been porting the Kessler scheme from CAM-SEMA into Emacs. And so Kessler is a very small microphysics parameterization. It's about 800 lines, including the metadata. And a lot of work has already been done to CCPP enable it. And so it's already modularized for us. We can just like pull it directly in. So far, I've written about 1,200-ish lines of C++ for our bridge code into Emacs, and that includes debugging code, comments, so that number's a little out of date, and then about 180 lines of Fortran for that bridge layer. I spent about 2 months-ish for the identity Stengel parameterization transforms, which was mostly just like combing through documentation and other examples, trying to figure out how it all worked. And then so far, we've spent about 3 months-ish bridging the Kessler code. I'll talk more about this later, but a lot of that was domain expertise that I lack, a lot of technical plumbing and validation work that's going on. And then we also did have to port Kessler into an OpenACC version to see how that would go. And And so this is obviously on like the coarsest grid imaginable, and this is not like a standard Kessler initial condition case. This is just with one of the EMXX aquaplanet initial conditions. So I wouldn't look at this as a confirmation that all of the physics are great, because I don't think that this is a real scenario. But this is just sort of a sanity check that if we run CPU, EMXX on the CPU with Kessler on the CPU, it looks very, very, very comparable to if we run EMXX on the GPU, transferring things to the CPU Fortran, or if we run everything on the GPU with OpenACC. So that's really nice to see. And then if we look at some other output fields, this is just for the lowest layer, we can see that we are getting pretty good alignment between the different hardware run that I did. They're not bit for bit reproducible, so we still have a little bit of work to do in there, but they are very close, which is nice and encouraging to see. And so since the theme of the conference is talking about the joy of development, the things that were really joyful about this experience was that EMXX has a lot of good examples actually for adding new processes, which was really helpful. So they have like a toy problem, and then they have all of their other parameterizations were very useful references. And there were also a couple of them that were very helpful for adding bridge code. So they had one that already had Python bridge support, and then another one that has a Fortran bridge. I mentioned previously that there are like decent built-in performance metrics, test suites, and like debugging sanity check features, which is nice. The developers have also been incredibly helpful, and I would say that the community in general has relatively good use for GitHub issues and pull requests, which are very helpful references. The things that were not joyful is that there's a lot of lacking documentation related to domain knowledge, which can cause a lot of confusion when you have no domain knowledge and you walk into it wondering, are these the same variables between these two different code bases? The answer turns out was yes, but we thought the answer was no for a long time. Not all of the compilers are necessarily well tested for all of the components and comp sets, because like the land model is developed by a different group and then pulled in. And so if we want to use OpenACC, we have to use the NVIDIA compiler, and that might not have always been tested for everything, which can be frustrating. I think also in general, this maybe isn't just E3SM, but I think that there's a lot of missing like full workflow examples of how do I start from here and then actually get a figure in the output. So I spent a lot of time emailing and bothering people asking, how do I do this one component? Because again, I'm not an atmospheric scientist like at all. And sort of the most recent thing that we've been working through is that the Cocos to OpenACC compatibility can be quite finicky. And so I think we've learned a lot, and now we know how to do it and work through it, but there aren't really very many other examples of how to get through this and make sure everything is talking correctly. So that was a challenge, but I think that we know how to get that working. And so I think the overall takeaway is that the language interoperability and bridging in this framework is pretty feasible and promising, but translating between different code bases can have some sharp learning curves. But I think that like once you kind of get familiar with it, it's actually not too difficult, and hopefully my documentation will be useful for other people if they decide to do this. But really briefly, next steps are obviously we need to verify Kessler in EMXX. So we're going to be using fKessler from StormSPEED. And so to do this, we need to use the analytical conditions, but I actually have that sort of working now, which is nice. And then we'd also like to add other CAM physics or other parameterizations into EMXX. So Kessler is pretty small, but it would be great to see how this experience goes implementing something like Club, which is quite a bit larger. We'd also like to explore other language bridging. So Python and JAX is up there. I think that one should be trivial. There's no examples currently for bridging with Rust and Julia, but I think that provides a very interesting opportunity for us. We've talked about doing some like automatic bridge code generation with like Claude and whatnot. And then obviously from a performance side, we would like to compare memory between StormSPEED with Kessler and EMAXX with Kessler, and also just general performance metrics like runtime, et cetera, across different hardware setups. So that's all I have. So if you have questions, I'm happy to take them. And then my sort of identity transform is available in a GitHub branch if you're curious about it. And otherwise, I'd like to thank the E3SM developers, Mark and Luca, who have answered a lot of my emails, and also Jesse for help with understanding how CAM and StormSPEED work. So that's all I have, and thanks.
Thanks, Ren. We have time for some questions. I don't see any in the Slido, but there's one in the room.
Since at CCPP, I have to ask a question. So CCPP is nothing, there's nothing in CCPP says that the physics have to be Fortran. It just happened so that all the physics in the models were Fortran ever since physics were written for models. And also there's nothing in CCPP that says that the interface that it generates needs to be Fortran. It just so happens that everything that we connected to so far is in Fortran. Mm-hmm. So in a sense, CCPP is basically a code generator like your bridge code that's based on common interfaces, which is described in metadata files for the physics and metadata files you add to the host model, basically taking away the pain points you mentioned, like, oh, is this the same variable? Does it have the same units? How is it decomposed? So I'm thinking if you wanted to do this with a bunch of physics that are all coming from CAM-SEMA, it might almost make sense to write a CCPP-like code generator for the language that you want, and then be done with it once and for all, because once you've coded up your host model metadata and you have your code generator, then it doesn't really matter so much which language you want to go back and forth. And you can do this for every single parameterization in the same way.
Yeah, that is something not like specifically that we've talked about, but as we've talked about the like automatic bridge code generation, I think that is important because, right, a lot of, at least from what I've looked at, a lot of the this is what this is either in the meta file or like in a comment in the code. And so I think in general, from like a community science perspective, it would be great to have these sort of files that exist anyways, just as like sanity checks, because I think even with domain knowledge, those are easy mistakes to make. But yeah, I think that there's a lot of, like, we can learn a lot from CCPP, that approach to like streamline this bridge code generation as well.
More importantly, you can add functionality that we don't have yet and that might be useful.
Yeah.
You know, and generate interfaces between different languages. That's a really good benefit.
Yeah, definitely.
More of a comment than a question. I don't know if you were at my talk yesterday when I mentioned a colleague who suggested that DOE could have saved a lot of money by, instead of translating codes from Fortran to C++, or in this case, adopting Cocos, instead paying compiler vendors to just offload Fortran's own GPU feature, which is do concurrent. The DOE community made this decision to develop Cocos and to translate a lot of codes about a decade ago, at which point the decision made a lot of sense. But we're not in the same place that we were before. So what saddens me is that, so I've been coming to NCAR every year, once or twice a year for about 15 years now, mainly because this has been a safe space where I didn't have to listen to the DOE religion that says everybody has to adopt Cocos, everybody has to move to C++, because a lot of the problems that you're talking about would completely vanish if Fortran codes were updated to use the language's own features. So if I want to switch from, say, OpenMP to OpenACC, I can just switch compilers or just change a compiler flag. And it's literally that simple. So none of the language interoperability comes up, none of the, translating things to, or, the ramp of learning Cocos comes up. We really are in a new place. Like, things aren't where they were when DOE made this decision. I can now write code that is pure Fortran that will run in distributed memory on 100,000 cores and automatically offload to GPUs with no MPI, no OpenMP, no OpenACC, no CUDA, no Cocos, anywhere in the software stack, just with the language. Mm-hmm. So I hope you guys can at some point start to push back. One of the things that's really ironic to me also is that whenever I go to the E3SM GitHub, it reports that something like 70 or 80% of the code is still Fortran. So where is all this C++ stuff that everybody's adopting? Because I don't see it making it upstream into the E3SM repository. Maybe that's one question.
Yeah, well, to answer that part of it, so they still maintain EAM, which is the Fortran version, and then they have EAMXX, and so there's like a different component that is the C++. So my understanding is I think they're still migrating to C++, different components iteratively.
I've been at Berkeley Lab for 5 years now. I've been hearing that story for 5 years, and I'm not seeing a shift in the GitHub.
Yeah.
I developed a set of slides that I would recommend taking a look at that I've used in a couple of talks that are online. I could give you links if you're interested. It started when I gave a talk at a big project meeting about a year ago to a group of nuclear science researchers. And I had heard that the community was beginning to move away from Fortran. And so the title of this talk, which I now have summarized in a couple slides, is "The Problem is Not Fortran." The main problem, there are some problems though. One problem is perception. It's that the people from outside the Fortran community don't really know what's happening in the language. They don't know what I just said a moment ago is true and has been true for several years. Mm-hmm. The second problem that I see is that the people inside the language also oftentimes don't know what's happening, and they're still writing Fortran 90 or at best Fortran 2003, in which case a lot of the younger people who are working on this stuff now are having to look at a language that was written before they were born, basically, like a version of the language. And the third problem for a long time has been compilers. But the number one thing I want to say is that has changed. It's no longer true. You can automatically offload Fortran without any of these other libraries that get mentioned in about 5 different compilers now. So we're in a new place, and a lot of the work and a lot of the churn and a lot of the effort that I'm hearing isn't really necessary, or at least it could be decreased a lot by just updating the codes.
Yeah, I mean, I spent a lot of, I know we're running into lunch, but my whole PhD was on performance, portability, and C. And a huge bottleneck was the compilers and getting those to cooperate. And so, yeah, I think that outside of atmospheric science as well, there needs to be a little bit more of a push for easing that entry, because I think it can be very overwhelming when you're like, I just want to do this one thing, and there's 5 billion flags, and I don't know how to do it, and I don't know what they mean. But yeah, I think that there needs to be more of an emphasis on compilers and bringing people up to date with those new features, because I definitely agree, like, people shouldn't have to bang their head against the wall getting OpenACC to cooperate with what they want to do. But I think that because people like to work in different languages, I think overall language interoperability is really powerful. Right, just from like an education standpoint, or just people work with different things. But yeah, I agree. I think people need to pay more attention to compilers and use that a lot more. Thanks.
Maybe I'll let everyone go to lunch. But yeah, I'll just say, maybe to defend Ren's work a little bit and to connect with Dom's point. I mean, from the standpoint of managing model like CAM or CSM or E3SM, I mean, we're now getting all sorts of different codes, right? We are getting physics codes that's written in Python or written in C++ or written in Julia, whether you want them to or not. And so I think we just got to figure out some methodology to accept all these different codes from scientists. And one of them could be just translating it into Fortran, or using C to glue everything together. But I think, at least at NCAR, we just don't have a good strategy for that yet. And so I think exploring all of these is helpful for us. So that was it. Okay, we can all go eat now. Thanks.
One last thing, one logistical question in the Slido is, can the person that was just speaking, so you in the back, share the presentation on "The Problem is Not Fortran"? Yeah. Yeah, so now we're at lunch and we'll reconvene at 1 p.m. for a tutorial. Thanks, everyone. Thanks again to all our amazing speakers from this session.
Okay, well, here we are back from lunch. Thanks everybody for coming back in. My name is Kate Rasmussen, and I work at Lawrence Berkeley National Laboratory. I work on a variety of projects related to Fortran, so you'll be seeing a little bit or a lot of that today. But I know that at NCAR there are more people maybe than at other institutions that still care about Fortran. So hopefully some of what I talk about today is relevant to you and what you do. Today, I'm going to be presenting idiomatic vibe testing with Julienne. And I would like to thank and acknowledge my co-authors, Damien Roussan and Dan Bonachea. Damien Roussan is here at the front, so he'll hopefully poke in when it's appropriate and when it's helpful. And thank you to both of them for their help with the slides and preparing for this tutorial. So here is an overview of what we're going to be exploring today together. We will start with a bit of a background to some concepts that are relevant to what we're going to be talking about today. And then we'll be diving into Julienne, which is the main software package that I'm going to be talking about today. And then we're going to look at some use case. So Julienne, just as a little preview, is a unit testing framework. So then we're going to look at a couple of use cases of how various software projects at Berkeley Lab use Julienne for their unit testing needs. So we'll explore that. And then we'll talk a little bit about RAG and vibe testing. What is vibe testing? We'll explore that later. And then we'll go through a little bit of a live walkthrough, giving you an example of maybe how you can use some of these things for your projects. And then because I do talk a lot about Fortran, and not everybody talks about Fortran at conferences, I like to sort of share some community-based information around Fortran to remind people that it still is a very vibrant community. So we'll end with a little bit of that. Okay, so I often like to start presentations asking some questions to get a read of the room. Normally I call that a temperature check, but because of the title of my talk today, I thought maybe a vibe check would be appropriate. So let's do a bit of a vibe check. So please raise your hand if you have heard of the phrase vibe coding. Okay, yes. Very good. Oh, and some hands online. I don't know that everybody can see that, but I can see that from where I'm looking at. So great to know that people online have also heard of this. Raise your hand if you have used AI to help you write emails. Oh, okay. Not as many. Well, let me raise my hand. I definitely have. I find emails sometimes more of a mental burden than they need to be as far as stress, and so I feel like that can help. But I always read what I'm writing, don't worry. I don't just send it off without any human in the loop. Raise your hand if you have used AI to help you write code. Okay, a lot more than the emails. Okay, great. Raise your hand if you used AI in a vibe coding sense, because I would say that the answer to my last question, just using AI at all, is different than actually doing vibe coding. So raise your hand if you believe that you do vibe coding. Okay, so less. And we'll explore what vibe coding is and talk about maybe the difference. But great, thank you for helping me set the tone. That is good to know more about my audience. So now let's go into the background. So idiomatic vibe testing with Julienne. There's kind of two topics that I'd like to explore for background that both sort of peel into the overall theme. So those two topics are vibe coding and unit tests. So first, let's explore vibe coding. So what is it? So I have a background in linguistics, and my framework for linguistics where I studied is communicative linguistics, not prescriptive linguistics. So prescriptive linguistics is much more focused on definitions and rules, and it's much more prescriptive, like this is the right way and this is the wrong way. My field was more focused on communicative linguistics, so it's much more about context and communication and are you succeeding at communication. So that means that for me, when it comes to language, I'm not the type of person that will be like, oh, you use that word wrong. Because language, natural language that we use on a daily basis is very dynamic and it changes and people use it in different ways in different contexts. So that is all to say that when I'm going to define the word vibe coding right now, this is what I view vibe coding as right now. This is maybe a more common definition, and I would say that some of these definitions can be used and sort of codified. If there's a very strong consensus on what a definition is, these things can be codified, put into things like dictionaries. So this is what I believe the sort of current accepted definition of vibe coding is. But with language, with all types of language, these things change. And especially with language when we're talking about fields like AI and LLMs, where the field itself is changing very rapidly, these things could change. And also even now, people could be using this phrase in slightly different ways. So this is what I am going to set the scene for vibe coding definition, which is that it is, so I would view AI and AI, like I would view code development that is enhanced by AI, or the usage of LLMs in particular is most common, as sort of a spectrum, and that on either side of the spectrum, you would have like more human involvement. And then as we get to the center, it's less human involvement, more AI involvement. And on the very other side, we have almost all AI involvement and not as much human involvement. My understanding of vibe coding is that vibe coding is pretty far along the spectrum on the side of more AI involvement and less human involvement, which is why I distinguished earlier between have you used AI when developing code versus do you do vibe coding. As far as I've seen vibe coding used, it means development of code where the AI is the primary writer of the code and the human is there in the loop, but barely. And this term actually, interestingly enough, was first coined just last year. And it was coined by Andrej Karpathy, who is an AI researcher. And I believe the first known usage of it was in a tweet that he tweeted. And apparently, this is a rumor, the thing I'm about to say next, because I didn't have time to find a citation for it. But I believe I have heard rumors that there was a dictionary entry of vibe coding just 1 month later. So this term was used and has quickly become part of the verbiage that we all use. So one of the main things, though, about vibe coding is that it significantly lowers the barrier to entry for non-programmers. So what are the pros and cons of vibe coding? I think one of the main pros is accessibility. As I just said, it lowers the barrier. So more and more people that would not have previously had the skills or knowledge or time to gain that skill and knowledge to write programs now can do a lot more than they could without the usage of AI. So we have a lot more people that are then able to participate. One of the big cons, I think, is probably one that we've all thought about. It's one that has come up many times this week. We've heard a lot of discussions about AI and LLMs in many talks this week. So one of the main concerns would be reliability. And again, a lot of these things has already come up this week, but when you have vibe coding, you could be having the LLM spitting out just hundreds and hundreds and hundreds of lines of code. And it would take the human who is in the loop, longer, like a huge amounts of time to read every single line of code and verify that it does what you want or that it's secure and safe, all of these things. It can be a huge burden. So people don't always necessarily read every single line of code, or they may not be able to read and understand every line of code if they are one of the people who's using it with less of a background in programming. So accessibility, yay. Reliability, concerning perhaps. And just on that, I would say that vibe coding, anytime that you might Google the term vibe coding and then look at news articles, you'll probably see new stuff. Like I said, this is a relatively new phrase. AI and LLMs are moving so fast, and a lot of people have a lot of opinions about these various things. So these are just a couple of news article headlines that just I saw within the last couple of weeks while preparing for this presentation. So one, the vibe coding effect, Apple's App Store saw 84% jump in new apps in quarter. So I believe that this has been stressing out Apple a little bit in terms of their ability to review all of the apps that are being requested to enter the App Store, because an 84% jump is obviously hugely significant in their ability to go through the normal processes that they would with onboarding an app to the App Store. So that's a big effect that we can see from vibe coding. And then also potentially related is that we have also seen news articles talk about how Apple is maybe blocking and removing some apps themselves that help people do vibe coding. So, feel free to audit these headlines for yourself, but or these news stories for yourself. But clearly it is something that is impacting a lot of things in the way that we work. And then also as users, maybe yourself have used some products lately where you've seen some more errors or bugs or weird things going on that you didn't expect to, even in not necessarily in like our scientific software code, but even just in like your email, maybe things are being a bit buggy. And I've heard just anecdotally some people going, I wonder if this is just because of a huge increase in vibe coding code that is out there in production. These are all things that we're going to be seeing how they play out as time goes on. But the reason why I'm talking about vibe coding today is because later on we'll be talking about the use of natural language idioms in programming language software that I'm going to be presenting. And the reason why that's relevant to vibe coding is because when you prompt an LLM, you're using natural language, right? You're speaking to it in the natural language that you speak. I'm currently speaking English, so if I was to write a prompt to an LLM, I would use the English language to prompt, right? But as I mentioned, did I mention this earlier? Anyway, as is true, natural language is ambiguous, right? And it is dynamic. That is something I did mention earlier, and it changes. So how does that affect the responses that we get from LLMs? That's something that Damien and myself are exploring in some research projects, and that we'll talk a little bit about today. But while you have ambiguity in natural language, you don't have that in programming languages because the computer has to know exactly what it needs to do, so it can't therefore be ambiguous. So we're going to explore how maybe the usage of natural language idioms through software packages in like Julienne can be used then with things like vibe coding, and how that might affect responses from the LLM. But more on this later. So the next background topic to discuss is unit tests. And I feel like a lot of people know the basic ideas of why unit tests are important, so I'm not going to go into too much detail, but the basics of what the most important message I want to send about unit tests is they're important, and like, they're important. And the reason why I go is because anecdotally from my experience and many of my colleagues, I think they're underutilized in scientific software. Damien and I get pulled in to talk with a lot of different scientists that develop software. So we get a peek into a lot of different projects that we may or may not eventually get involved with and help for whatever reason why they want to talk to us about. But anecdotally, I see a lot of software out there that has very minimal testing or no testing at all. And as software developers, myself and Damien, and certainly hopefully many people in this audience, believe that that's not great and that more unit testing, more testing in general, is better for our software. So hopefully we're all on the same page there. But a little bit more about unit testing that I wanted to discuss is the idea of test-driven development. So with test-driven development, you write tests first, and you write tests as if they're specifications for the source code that then is supposed to be used with the test. So you write the unit test first, and then you go write the source code, and you write the minimal passing code to get that test to pass. And then once that test passes, if you need another functionality in your source code, you then write the next unit test or expand that unit test, and then go back and write the minimal passing code in the source, and then rinse and repeat, etc. So that's the idea of test-driven development, and we'll see why I wanted to bring that up a little bit later. But ideally, with your unit tests, you have suites that can run in seconds or minutes, so that it can be a really frequent part of your development process where you make changes to the source code, run test suite to see if you broke anything. Make changes, run test suite. Make changes, run test suite. Make changes, run test suite, right? So if you're running a test suite that takes 30 minutes, that's not going to be very easy to integrate into your development. But if it's quicker, that's great. That could be very useful. And then hopefully you're also able to be utilizing things like CI, where before you ever push anything to some remote Git repository, you're running your test suite, and then you push your changes, and then hopefully also the CI there on the remote Git repository is also running integration tests or whatnot. So those are some ideas about unit testing that I wanted to share. And in addition, I wanted to talk about correctness checking. So assertions in unit tests or in source code can be used to verify expected behavior. And this is very important to check that your preconditions, your postconditions, and your invariants are occurring as expected. Does Julienne provide assertions? ? I wonder what the answer to that could be, but we'll see more later. Very leading questions. So now let's talk a little bit more about Julienne. And I wanted to mention at this point in time that I did present on Julienne and another software package last year at this conference. So some of you might have heard me talk last year. So I'm going to be covering a little bit of the same ground because I wanted to make sure that I give the correct context for those that didn't see me talk last year. But for those that did, please don't worry. There's a lot of new things that have, a lot of developments that have happened to Julienne that actually mean that the last year's content on how to use it is a little bit, it's just out of date, and that if you want to use the current versions of Julienne, you would need some of the information that I'm going to share with you today. So there are exciting new developments, and hopefully there won't be too much repeating. But just to then now present what is Julienne, here we have some lovely pictures of vegetables that are being sliced. And as I said last year, something that we frequently hear is you have to eat vegetables, right? That's just a mantra that we hear in life because I think it is true scientifically, or at least it helps, it aids the human body to eat vegetables. We'll say that. I'm not a physician or anything, but some people love eating vegetables, so that's all grand with them. Some people hate it and do it just because of the health benefits that it can give you. And I kind of view unit testing in a similar way, is that unit testing, as we have just discussed, very, very important. Some people love writing unit tests. Are there many of them out there? Who knows? Who's to say? I've never taken a survey. But I think a lot of people don't like writing tests. They'd rather write source code. They'd rather get into, whatever scientific thing that they're working on, and they don't want to worry about tests. But you have to eat your vegetables, right? And maybe you also have to write unit tests. So Julienne was inspired by a package called Veggies, which is a unit testing framework, which has the similar reason why it's named Veggies is because you have to eat your vegetables to make, the human body better. You should be also writing unit tests to make your software better and safer and secure. So eat your veggies. Julienne was inspired by Veggies, and therefore the name Julienne is also inspired by the name Veggies because Julienne is a noun or a verb that it refers to slicing vegetables in a very thin manner, as you can see on the screen right now. So Julienne, as you can see here, is a lightweight utility. It is a unit testing framework that is inspired by Veggies. So let's write unit tests. So a bit more background about Julienne. It began as a Fortran unit testing framework, as I mentioned, but it has grown a lot, which is some of the growth I talked about over the last year. It has grown to support natural language idioms for assertions inside of user code and also tests external to user code. And we'll be talking more about that later. That's very important to the theme of today's talk. Tests in Julienne can be single or multi-image. We'll explore a little bit of that in a second. And there's also a really useful scaffold program that Julienne provides, which allows you to get set up with starting it gives you some boilerplate on starting a new Julienne test suite that can help you get started. And we'll also be exploring that later. Now, Julienne tests, you can write them in a way that then the tests themselves can kind of be read as a specification. And I think we'll also explore why that can be helpful. And the last brief thing is that Julienne is an FPM package. And we'll talk a bit more about FPM right now. So if you were here on Monday and saw Damien Roussan's talk, you would have heard him laud the wonders of FPM and how it has saved him many a headache. And I agree, FPM is really great and has also saved me a headache or two. But just to explain a little bit more about what FPM is, it is a package manager and a build system. It is written in Fortran itself, which means that it is maintained by the community that would use it, right? It is a package manager for Fortran, for software written in Fortran, but the package manager itself is written in Fortran. So the people that would use it are also the people that then know the language well enough to be able to go contribute to FPM itself. So that's great. I think it has a really vibrant community because of that. What's so lovely about it is that it automatically detects file dependencies. I think Damien mentioned a bit of this the other day. It can build Fortran C and C++ code, and FPM itself is very easy to install. So now that we have discussed a little bit about what Julienne is, let's begin looking at the ideas around what is the Julienne test output, and we'll see specific examples of that soon. So Julienne output includes a test subject, which describes what you are testing. Often you might use Julienne to test a specific class or a type-bound procedure. Julienne output also includes the test description. And it also then will say whether it has passed, failed, or skipped, and what skipped means we'll also discuss later. And then it gives diagnostics. If the test fails, it will give you additional information to help you diagnose what the problem might be. And we will most certainly see more examples of this soon. Okay, so I mentioned that Julienne can be either in single image or multi-image. So Julienne can not run tests in parallel, but it can run parallel tests. And that is to say that it can run tests that include Fortran source code that uses the parallel features, the native parallel features of Fortran. such as like co-arrays and collective subroutines, etc. So with that, when you use tests that invoke the multi-image Fortran features, every image will run every test and only report that a test passes if it passes on all images, and then only image 1 will output the test outcome. So here, because I did talk about Julienne last year, I wanted to upfront say some of the developments that have happened with Julienne, and that is expanded compiler support. I know that people that develop actively in Fortran sometimes have a couple headaches or two related to compiler support for various features. And so when we are able to support lots of compilers, that makes us happy. And so just wanted to show that. And especially L-Fortran, if you don't know about L-Fortran, it is a compiler. I think also David mentioned this compiler on Monday. But if you don't know about L-Fortran, please look it up and learn more. More open source Fortran compilers out there is always great. So we like to, let people know about it. Damien. You have to push the button. Damien, sorry. You have to push the button so you can hear.
Sorry, I promised Kate I wouldn't jump in unless she asked me to, but I helped her with this slide, and I just realized a mistake that I made, which is that we forgot to include L-Fortran, so I'm really glad Kate mentioned it. So we have only 5 compilers listed here, but you actually have 6 options.
Oh, but L-Fortran is on the slide.
It's the first one.
Yes.
Sorry. Glasses on.
So in fact, you did not make a mistake, David. Thank you very much. But thank you for jumping in. Feel free to jump in whenever. And then we have also expanded parallel testing. That is because LLVM flang, now we can have LLVM flang call Prif and Caffeine and GasNet. And what that is a whole nother conversation that we'll touch a little bit upon today. But if you have questions, please do contact us because we have a lot of things to say about that. But just to note that there's expanded testing that is available for the parallel features. And then the scaffold program that I mentioned, that is new and very, very helpful to get you started. So we'll see that later. And then there's also been addition of a test diagnosis T-string concatenation operator. We'll also see how that is used later. So I won't go into detail now, but that is new and very useful. And then the big, big difference is that there have been introduced these idioms, and they are used as a unifying theme across 2 disparate technologies, which are unit tests and assertions, but they both are very useful. And we'll describe what we mean by idioms and how to use them soon. And by soon, I mean I need to take a break to drink some water. Okay, so what are Julienne idioms? Here we have a little bit of code. This is just one assignment statement on multiple lines because it's a bit long, but it's just one assignment statement, which is providing the result to a unit test function in Julienne. So the right-hand side of the assignment statement is an expression that will eventually evaluate to either this test passed or this test failed, essentially. And so just to read it, it says test diagnosis also. All actual course approximates expected course within crude tolerance. And then there we have the concatenation operator, course grid, second order Laplacian sin sub x. So where are the idioms in this? One might ask. Perhaps you're asking yourself this question, or perhaps you're asking me this question at this very moment. And here's the answer. Hopefully the colors are different enough to see that the things highlighted now in sort of navy blue are the Julienne idioms. So we have dot also, dot all, dot approximates, dot within, and then the concatenation operator. And so this is something that is really cool about Fortran, and that I know Dave really likes to talk about this subject, so sorry to steal the theme from you. But one thing about Fortran, so many languages, you can of course overload operators that exist in the language so that it can operate on specific types that you have defined or do specific things that you want to do. With Fortran, which this I believe does not necessarily exist in a lot of other languages, Fortran allows you to, of course, overload existing operators as well. But it also allows you to define your own operator and come up with your own spelling for what that operator is. So that allows us, as developers of some of these packages at Berkeley Lab, to do what we are meaning when we say natural language idioms in our programming, because we are defining operators that are, they are spelled out as, language. We're not just using characters, like a less than or something. We are defining our own operators that use English spelling to define new operations, and so we can define things that read like natural language and that are then in that sense more idiomatic. So we'll explore more about the operators and what they can do for you now. So we have a less than operator. And it is spelled less than, x less than y. We have a greater, these are all idioms in Julienne. We have a greater than operator, as you can see, spelled greater than. We have an equality operator, which is spelled equals expected. But with this, the thing to note is that it is asymmetric, right? So I equals expected j is not the same as j equals expected I, which is different than perhaps, I'm pretty sure, than the equality operator in Fortran, like the one that the language defines for you. There's a greater than or equal operator, which is spelled is at least. A less than or equal to operator, which is spelled is at most. This operator helps you verify alphabetical order, so is before. Reverse alphabetical order is after, so this operates on strings, characters. And so all of these above operators operate on intrinsic types from Fortran, so things like numeric types, character types. One of these operates on type C pointer. For more details about which operators operate on which operands, please check the README at that URL if you want more information. But one thing to ask is, well, there is a less than operator in Fortran, for example. So why this? And why are you not just overloading? So, well, one answer to that is because we might want to use these things on types that Fortran doesn't allow you to use those operators for. But then why not just overload the Fortran operator for less than? Why spell out your own new one? And the answer to that is that when you are overloading operators, there can be some confusion in which contexts which operator might be used. Again, not necessarily for the machine, because those things have to be unambiguous, but for the reader of the code and the writer of the code, you can get sometimes confused if you're just overloading operators, and then that can lead to bugs and stuff accidentally introduced. So when you're defining your own operator, then that makes that much more clear. And with Julienne, there are reasons why, for the testing purposes of it all, that these operators are important to have been defined. And then additionally, which we'll explore a little bit later, as I said, these operators are mimicking natural language, so that will come into play later, and some ideas that we have on that. And then the last thing I wanted to say about these is that these above expressions return a test diagnostic T object, and so that object will basically tell the rest of the framework whether your test passed or failed. And we have some more operators. So there's an AND operator, which in Julienne is spelled also. And this operates on test diagnosis T objects, and then it returns an object of that same type. And that allows you to put things together, so you can have an expression like this: I less than J, also K equals expected M, right? So if I'm using that to assign to a test diagnosis T object in a unit test in Julienne, then that test will only pass if I is less than J and also K equals expected M. There's also an all operator, which helps provide some functionality related to arrays. And then there's a logical operator. So you can ask it to, so for example, allocated is an intrinsic function in Fortran, and so it will return true or false. So you can say expect true. And so if it's not allocated, then it will say, then that will return as false, and then it will evaluate to something false. And then, as mentioned before, this concatenation operator. Okay, now this is also exciting. These are the last operators that I'll introduce at the moment, and that is that there are some operators that allow you to check equality within a certain tolerance. So if you're not, looking at integers, if you're looking at things like reals or double precision in Fortran, you can say something like x approximates y within tolerance. And then there's also within fraction or within percentage. So that is really great because if you're comparing two reals, obviously, and you just use a normal equality operator, that's not necessarily always going to give you what you want. But now you can compare them within a specific tolerance using these very, very nifty idioms in Julienne. Okay, so now returning to what we had seen earlier, now that you've learned a little bit more about Julienne and its operators, we can see that this test reads like a specification, and that is similar to natural language sentence, but this is all, things that are happening in Julienne to verify behavior in your code. Okay, now back to that question I posed earlier, the very leading question: does Julienne provide assertions? And the guess is, the answer B is Yes, but of course, yes. Julienne, of course, provides assertions, or else I wouldn't have asked that question. So it provides assertions using the following spelling: call Julienne assert, and then you pass it an expression. But what is really great is that this can be compiled away. So if you're running your code in a production mode and you don't want it to have all these extra, all these extra cases, then you can compile that away. And that is the default, actually, that is compiled away. But if you then want to run in debug mode because you're facing a problem and you want to check to make sure that all of your assumptions about your code are true, if you have used Julienne assertions, then you can just activate those assertions using the deassertions preprocessing compiler flag. And then your program will, keel over and die if it hits any of those things. And so that is very useful for debugging. So through the usage of this Julienne assertions, you can then assert those preconditions, postconditions, and invariants that we talked about earlier. And these assertions are frequently used in source code, but you can also put them in your Julienne unit tests. Okay, maybe another breather for water. I don't know if Damien wants to tell a knock-knock joke. No pressure.
I'll mention, Kate talked about how easy FPM is to install. I would say it's probably the easiest package that's ever received. Also, every time they release it, there's a list of release assets, like binary expressions, one of the release assets is always a single file that has all of FPM.
Oh, can you use your microphone?
Shoot. Sorry. Thanks for the reminder. So I was saying FPM is probably the easiest package I've ever seen to install. Like people, when they first hear about this, they're like, oh, I don't want to learn a new build system. Well, there's not much to learn because I showed you a 3-line version yesterday and it was like, oh, I don't want to install something new. Well, there's not much to do to install it. Every time they release it, there is a single file that contains all of FPM concatenated into one file. You compile that one file and you have a working installation of FPM. Done.
Yes. Thank you for that aside. I appreciate it. So let's look at our first use case. And just to say up front that for these use cases, I'm going to be briefly describing what the software packages do. And these are all software packages that are developed by at Berkeley Lab, and the lead developer being David Roussan. So I will briefly describe what they do, but I'll mainly focus on showing examples of how they use Julienne for their unit testing needs. But if you have any questions about any of these software packages, or are you interested in talking more about them, please do find us after or contact us, because we always like to talk about things like the software that we develop. So first is FIATs. And FIATs is an acronym that actually stands for two different things, neither which is related to the car, but for some nice pretty images, I have chosen to use that funny relationship between the word Fiat, which is a car brand, and the name of the package. And it is also relevant because we are talking here about deep learning and, doing things fast, I suppose. And so cars are fast, one can also say. So anyway, some cars. So FIATs is a deep learning library that uses Fortran. So it does machine learning and it researches AI's impact on HPC. So FIAT stands for Functional Inference and Training for Surrogates. The alternate name, because Damien was smart enough to come up with two names, is Fortran Inference and Training for Science. So FIATs does training and deployment of neural network surrogate models for computational science and does automatic parallelization of batch inference. FIAT does use assertions from Julienne, and what it uses those assertions for is to validate that the input data is in the correct format. So in the source code, when FIAT is going to construct an object and read the data that it needs to construct the object from a JSON file, then we are using a lot of Julienne asserts there to validate the JSON input data before we try to construct the object, obviously, which is great, because then if there are problems, we catch them right away as opposed to later down the road. So it basically validates the construction of the layers of the neural network. So let me move this Zoom window. Sorry if I can see that side of my screen. Okay, so what do FIAT's unit tests need to do? They need to ensure that an object, among many other things, but for example, they need to assure that an object of type neural network T that encodes an XOR gate can correctly perform elemental inference with the step activation and one hidden layer. So that is one unit test, just as a sneak peek. It also, did that switch? There we go. It also needs to verify that an object of type neural network, et cetera, can correctly perform elemental inference with the ReLU activation function and one hidden layer. And then also that all of that can correctly perform elemental inference with 2 hidden layers. So just an example of all of these little things that we have a derived type called neural network T, but there's a bunch of different functionality within that derived type that Fiats need to verify that it works correctly. And so Fiats uses Julienne unit tests to help validate all of these behaviors and much, much more. But so what does a Julienne unit test look like? So a Julienne unit test is basically one function that returns an object of type test diagnosis T. So here we have an example, and that is the entire unit test function for one unit test of the unit test collection that tests all of the different functionalities for the neural network T derived type. And to zoom in a little bit on the meat of the function is this assignment statement. So again, we're assigning to a test diagnosis T object, and then we have that very long expression on the side, which determines whether the test has passed or failed. So we're checking that all of the truth table values in the first part of the array approximate false with intolerance, and then all of them within the second value in the array approximate true with intolerance, and et cetera, et cetera, et cetera. And that also operator is there to make sure that all of those things have to evaluate to true to be able to have this test pass. So then this is an example of what the code looks like for one unit test collection. So we can see here in the we have an array sorry, I need to move around the Zoom window again. We have an array of test descriptions, and on the first one we have, it says elemental infer one hidden layer XOR step is the last part of that line, and that is referring to this function that I showed you on the last slide. So you can see that that one unit test that we saw on the last slide is then inserted into this array of unit tests. So that's why I'm referring to this as a unit test collection, and all of those are all of the unit tests that then test that singular derived type in Fiats, the neural network T type. And then all of that gets packaged up together and then passed off to a driver, and the driver will run all of the unit test collections and then give you output. So, sorry, yeah, there we go. So what does that output look like? Well, just to zoom in on what the output just for that one Julienne unit test collection is this. You can see that we have the first line describes the unit test collection itself. So everything in that unit test collection is checking that a neural network T type object can encode an XOR gate within those specific different cases. So each of those is a specific unit test, and we can see that it reports whether it passed or failed for the purposes of this. Well, the test passed, or else they wouldn't, we'd have to fix the code and fix the bugs. So when I ran the unit test suite, we can just see that they all pass, which is great. And then you have a little report at the bottom for that unit test collection. It reports how many of them passed and how many of them failed, if there were any failures, and then how many of them were skipped, which we will explore later. So just to look a little bit more at what the output of Julienne gives you. So again, I mentioned that that first part is the subject of the collection of the unit tests. So now we have multiple unit test collections on the same screen, the output from those on the same screen. So you can see those parts that I have highlighted in the little box are all of the subjects of the collections of unit tests. And then here I have highlighted just a single unit test description. And so you can see that it describes the expected behavior, and it describes whether it passed or failed. And then at the bottom, now this is just an abridged part. The test suite for Fiats is longer, and so it wouldn't have fit nicely all on one slide. So this is just the bottom part of it. So it's a little bit abridged. But here at the bottom, you can see that after all of the different collections of unit tests have run, then it's all packaged up. So you can see the total amount of tests that passed or failed and how many were skipped. And then there's also a little bit more information about how long the test suite took to run, and then the number of images that you ran it with. And I just ran it with 1. So an example of Julienne assertions, if you're interested in using those, I wanted to show you an example. So again, as I mentioned earlier, assertions can be used in both source code and tests. And in source code, in fiats, those assertions, as I mentioned, are used to validate the input data before you construct the objects. And so here I have highlighted in blue just what you need to use the assertion. You just say call Julienne assert, and then you have an expression that you are asserting. So that expression can be as long or as short as you want it to be. And again, that line of code, under the hood, it's all different types of macros and stuff, but that line of code will be compiled away to nothing if you don't use the assertions flag, which is great for when you're running in production mode, but when you're running in debug mode, pass the flag, and then those assertions will run and either drop down dead if you do have a problem, or everything will be fine if those assertions don't fail. Okay, another breather. Sorry, I have to plan these out or else I will go for a long time without drinking any water. That wouldn't be great for any of us.
So while you take a break, I'll mention there's actually a third meaning to fiats too. So the first meaning was functional inference and training for surrogates, because we're focused on surrogate models for science. The second one you only say amongst friends, which is the Fortran inference and training for science, because we can't always mention Fortran in some settings. But the third one is a fiat is a decree, or let's say from Webster's dictionary, an authoritative or arbitrary order or decree. Now, why would you want to name your software that? This is deep learning software, it's AI. That's kind of a cautionary note about whether we should believe everything we get from AI.
I like that, thank you for that. I actually not sure if I had known that that was a third reason for the name, so that's great. Okay, so our next use case is caffeine. I have caffeine over there that I would like to drink, but I don't want to accidentally knock it over while I'm gesticulating and spill coffee on my computer, so I will go without caffeine, but we'll talk about the software caffeine. And the reason why I wanted to talk about caffeine today is because the unit testing needs for caffeine are significantly different than what we just saw in fiats, and different than, I think fiats was written with the idea that you would probably be using those unit tests collections to verify things related to a specific drive type. But caffeine has unit testing needs that are very different. So I wanted to just show you a different example so that you can see that you can use Julienne in different ways, and you don't have to be siphoned into just that one style of testing. So what is caffeine? Just for the brief overview, caffeine stands for, again, another acronym. I've never met anybody in my work life that could come up with acronyms like Damien, so which is great. I don't have to do any of the work then when we're naming software. I just say, hey, Damien, use your skills, please. And his skills were used to name caffeine, and it stands for Core Fortran Framework of Efficient Interfaces to Network Environments. So a bit of a mouthful, but if you know Damien, then you also know that he loves coffee, particularly espresso. So caffeine is just a lovely theme in general. But caffeine is a runtime library that supports the parallel features of Fortran. And so it does that by implementing PRIF, which is the parallel runtime interface for Fortran. I won't go into what all that is, but it is something that is very important to the work that we do. So if you have any questions about that, or if that sounds intriguing, again, please do contact us. We'd love to talk. But yes, it basically supports so if you have a user that is a Fortran user that is writing source code that writes that uses source code that uses parallel features, the native parallel features from Fortran, then you obviously need a compiler and a runtime library that can support the execution of those. And so caffeine is the runtime library for that. And currently, LLVM Flang lowers some calls to PRIF. So if you link LLVM Flang to the library caffeine, then you can actually compile code using LLVM Flang that uses the Fortran parallel features, which is really great and exciting. And then we also are looking at being able to hopefully do the same with Fortran. So keep your eyes out for that if you're interested. Okay, so as I mentioned, caffeine's unit testing needs are very different. There's not just the code base, the source code base for caffeine is not, sort of just based on a bunch of drive type objects that then make up the software in the same way that fiats is. There's a bunch of different drive types in fiats that then make up the conceptual neural network. But caffeine is very different. Caffeine, as I said, is implementing features that come from the Fortran language itself. So caffeine rather just needs to implement that. Caffeine needs to verify that its implementation of something like num images, prif num images because of the prif part. But so caffeine has a prif num images function that the caller can call, and we need to verify that when somebody calls prif num images, and that's the compiler, right? Users don't write prif num images, but the compiler will call prif num images, and we need to verify that caffeine is fulfilling all of the language expectations that are specified in the Fortran standard that come along with num images. And all of the other things, including core rate allocation. So caffeine has a bunch of routines that the compiler will call to support the named sort of functions and subroutines in Fortran that provide parallel features such as num images or collective subroutines or synchronization statements. But then we also have to support core rate allocations. So those are not functions or subroutines in Fortran. They're different types of statements, but then caffeine has their own functions and subroutines to support core rate allocation. So we also, our unit tests have to verify that caffeine is correctly performing core rate allocation, and core rays are distributed memory objects. So we need to make sure that that our routines are successfully allocating symmetric and asymmetric memory. So there's a lot of things to test, and then we also have to test that the remote memory access routines that caffeine provides are successfully putting and getting data on other images. So again, caffeine uses Julienne unit tests to validate all of these behaviors and much, much more. Okay, so here's a little quick look at a caffeine test. And again, you don't have to read the entire thing, but the most important part I have highlighted in blue at the bottom, which is that equals expected idiom, right? So in this unit test, we have a bunch of different setup that this unit test has to do so that caffeine can set up the environment in which to then be able to test that the retrieved value is equal to the expected value. And this one is testing RMA, remote memory access. And so very important to make sure that we're doing that correctly. And there's all that set up, and just that one line allows Julienne to verify whether that is working correctly or not. We also have tests that are verifying that we can test out of memory errors during core rate allocation. And so here I have highlighted again the equals expected idiom from Julienne is being used to make sure that this error stat message that we get back that says out of memory, we purposely run out of memory, and then we make sure that we're actually getting an out of memory error stat message. And then I just also wanted to mention that caffeine has a special function like macro that Julienne doesn't have, but we have discussed on whether Julienne might adapt this as well. But caffeine has a function like macro that it defines that allows it to, this function like macro expands to, in the sort of the middle top right, the also expr expands to diag equals diag also expr. So we're using that dot also dot operator from Julienne, but we just put it in this macro so that you can write it in a little bit of a simpler way. But basically you can see that we're testing a lot of different things in our state. We're testing this, etc. I won't go into the details, but we're testing all of those things to make sure that all of those things are happening correctly. And if any single one of them is not happening correctly, then you will get a test failure. Yes, please. Absolutely.
I'm not sure the also there. Does that mean every also does that thing? I'm not quite sure how that works.
Yeah, so I don't know if I think you can see the numbers. So on line 388, well, actually, let's look at line 383 first. So on line 383, you have diag is equal to true. Right. So diag is of that type that I've mentioned a bunch of times, the test diagnostic T type that comes from Julienne. So diag, that variable diag is going to be telling Julienne whether the test passed or failed. So for this test, we start off with true. So we start off with yes, true, and then we have a bunch of different things where on line 388, that also in capitals and then the expression afterwards is a function like macro. So that will expand to diag equals, and because we already have diag defined, that will expand to diag equals diag also, and then the expression that we have within the parentheses in the function like macro. So it just keeps, exactly. You're basically just, adding that to the expression over and over again. Well, evaluating it each time. No, thank you so much for the question. That is, I didn't point out line 383, but that does help make it all make more sense. And again, just as a note, that also function like macro is not available in Julienne. That is specifically something that one of our, Dan Bonate, our colleague, made for caffeine, because he was doing also very frequently, and he loves a macro. So he made that possible. But it is something, like I said, that we've discussed integrating into Julienne, because Julienne could easily provide that as well. So if anybody thinks that that's great and wants to, ask for it, feel free to contact us and we'll see where it goes. Yes, please.
Sam, and I think it said, does it have to be named, sorry, in the last slide, does it have to be named diag, or does it look for any type that's test diagnosis type and do the also logic?
That is a great question. It does have to be named diag, and because this also function like macro is defined in caffeine itself, the caffeine test developers know that that macro will only work and expand and do what is expected if you have that variable be named diag. With Julienne, of course, you can name your result of a unit test. You can name it whatever variable you want. That's absolutely doesn't matter. But with this expansion or this function like macro within caffeine, you do have to do that. So if we were to integrate this functionality into Julienne, we'd probably need to explore more how that would work, because not everybody's necessarily going to name their variable the same name. So great question. Okay, so just to zoom out then a little bit, the same way that we did with fiats. So here we have what the unit test collection looks like. So again, we have an array of test descriptions, and so which includes the test that one of the tests that we just saw. And so all of that will then be packaged up and passed off to the driver, and then everything can be run. So, and this is just an example of the other unit test collection, but I think we've got the point. There is something here that is interesting that is different, but we're exploring that later. So I will move on from that. And I have another pre-planned break. So Damien, feel free to say if there's anything else you want to share.
I thought I had a correction, but I was wrong. Kate and I have been working together really closely for about 8 years. I always tell her it reminds me a lot of a relationship with working relationship with someone I've worked with for about 20 years, Carla Morris, who's at Sandia National Labs. And Carla told me that at some point in working with me, she would just kind of say to herself, okay, I wonder how long it'll take him to realize he's wrong this time. I was about to jump in and correct her, and then I realized I was wrong.
Thank you. Okay, so now moving on to our final use case, which is formal. So formal is a newer, relative to the other packages that I've talked about, a newer package at Berkeley Lab, and it stands for Fortran Mimetic Abstraction Language. And we'll talk a little bit about why it's called, why mimetic is involved in the name, but I, again, kind of use that cheekily to then have a fancy picture of mimes. So formal provides derived types and mathematical operators that mimic vector calculus. So just in the way that with Julienne, we have these defined operations where you can spell out exactly what you want in the operator that you're creating. Formal defines its own operators, but it defines them to mimic vector calculus. So that is also another way that then we can write out code that uses things that look like natural language, but that very carefully or very closely relate to the actual like mathematical functions that this vector calculus is derived from. Anyway, so it supports the formal verification of numerical algorithms, and it is actually a foundation for an embedded domain-specific language. And this is a big project for Damien. So if you have more questions about formal and what that is doing and the embedded domain-specific language, hopes for the future and all of that, please definitely make sure to talk to Damien. So here we can see a lovely picture that Damien provided. Thank you very much. But here you can see the mathematical operation, and then you can see below the code which uses these defined operations to then perform the same math. And so formal facilitates a degree of expressiveness that mirrors textbook notation, and it guarantees the satisfaction of important vector calculus theorems. And again, for more information on that, please do contact my colleague, Damien Roussan. So unit testing wise, to focus on that a little bit, some things that Formal needs to do is verify the accuracy of the discrete calculus defined by Castillo and Corbino in 2020, in that article from 2020, and then Dumet and Castillo from 2022. And it needs to exercise Formal's defined operations, which here we have some examples of the .sss dot, which is a triple integral, and then dot, which is a dot product. I don't think I've ever said that out loud. I didn't realize that would be silly when saying out loud, but there we go. So here is, again, a unit test for Formal. So the majority of this you don't really have to read or pay attention to, or like focus on rather, but for the purposes of this, that is the test diagnosis. So just to read that out a little bit, because it's maybe a little bit small, test diagnosis also calculated order approximates expected order within percentage, order tolerance order, and then you have some additional information with the concatenation operator. So for convergence rate of ordinal order, order discretization of .sss v .grad f times dv. So all of that. And then we also here have just what the unit test collection looks like. Hopefully we're getting a little bit familiar with that pattern where you have one unit test and it's part of a unit test collection. And this unit test collection tests the set of second and fourth order 1D mimetic integration operators that Formal provides. Okay, now we're getting into the vibe coding and LLM ideas of it all again, and gonna hopefully tie some things together. So let's talk a bit about RAG and vibe testing. Now, many people said that they had heard of vibe coding. Has anybody heard of the phrase vibe testing? Okay, great. I say great because I'm pretty sure Damien's the first person to use it, or at least the first person in my known knowledge. Like I've never seen it anywhere on the internet or in articles or anything or at presentations. So potentially the concept of vibe testing is maybe something that myself and Damien and some of our colleagues are developing right now. So the future is, who knows what the future is, but let's just explore that topic a little bit. So RAG is a sort of an AI technique, and it stands for Retrieval Augmented Generation. And the basic idea of RAG is that it retrieves relevant data to augment an LLM's response. And I'm going to talk a little bit about a project called Astra AI, well, rather a tool called Astra AI that has been developed as part of Berkeley Labs' work within the AI for HPC team. And AI for HPC is a ModCon project. And if you don't know what ModCon is, it's a DOE project initiative related to AI, and there's a bunch of discussions about, so the Genesis mission that has been mentioned twice, once by Damien on Monday and once by another speaker. The Genesis mission is asking a lot of people to do work on AI related things for the DOE. So there's a bunch of proposals being worked on right now for that. And ModCon is kind of a little bit of a mini predecessor, I think, to that. But so the people at LBL that have been working on this are Sherry Lee, Mahesh Natharajan, Damien Brisant, of course, and myself. And there's the GitHub. If you are intrigued enough by what I'm about to say, you can follow that GitHub link to look at the tool. It is now publicly available, but it is basically a tool that uses RAG and some other techniques to support developers and users of scientific software. And we'll explore what I mean by that. So how does Astra AI use RAG? So Astra AI will, when you run the tool, you pass the tool a path to a local repository, which has source code that is annotated in comments with metadata. And that metadata, the Astra AI tool then reads that metadata and then will use LLMs to create embeddings. And then those embeddings will be important later. And your code can be annotated with metadata manually. So you can look at every single code. You can decide how you want to chunk your code, your source code up, and then annotate it with the metadata. Again, write comments. You can write descriptions of what the purpose of the function is or the code is, what types of types of types it uses. You can write kind of whatever you want in the metadata. And so you can do that manually, or you can use an LLM to generate the metadata if you trust it. Again, the idea of trusting LLMs is something that has come up many times this week, but that is possible. But so Astra AI then the next step in the tool, in the workflow rather, is that Astra AI, I already said that part, the embeddings. So then the next step is that you have then a user prompt that a user might write. So if you are, say you are a developer of scientific software, but you want to call a scientific library that you haven't used before, and so you want to very quickly understand how you can call it and what types of things you need to call it for to complete the tasks that you want for your personal scientific library. So Astra AI has been tested a lot with Amrex. So if you're a new user of Amrex and want to call into that library, you can use it. We've been testing it with Formal, which is why I just talked about Formal. But so basically, you imagine a scientist who wants to call a scientific library that they've not used before. They can write a user prompt that says to an LLM, hey, I need to do ABCD thing related to sciencey bits and stuff, and I want to use this library. And then you name the scientific library that you want to call. So when that library is the same library that Astra AI has previously analyzed to create embeddings related to the annotated source code, then Astra AI will take that user prompt, it will create embeddings based on the user prompt, and then check those embeddings against the embeddings from the annotated source code, and it will decide which code chunks from the annotated source code, which code chunks are most relevant to the language that is in the user prompt. And then it will create a new prompt for the LLM where it actually inserts directly those code chunks. So you'll have a full function or a full routine that Astra AI has determined is most relevant to the prompt. It will add that into the prompt itself, and it will also add in the metadata that was originally used to annotate that. And then you can also, or Astra AI currently add some other just sort of textual things like, imagine you are an expert in blah, blah, blah. So basically Astra AI then will augment the user prompt, and then you will obviously have the original user prompt and then pass that off to the LLM again. So then what the user gets of this Astra AI workflow is they just get the final response from the LLM, hopefully providing them with source code that calls the scientific library that they wanted to call, that then they can integrate into their code base. So all of that, which I just said, now there's a little bit of a workflow. This workflow image doesn't contain the creating of the embeddings based on the annotated source code. It just starts from the user prompt. So we have the user prompt, and it is of course written in natural language. And then the LM extracts the user intent, so it analyzes what the user is trying to do. It uses RAG to determine the most relevant code chunks, and then it creates a final prompt to the LLM, which the prompt contains the original user prompt, as I said. It supplements it with additional sort of textual things, and then it supplements it with the relevant code chunks and code metadata. And then it passes that whole thing off to the LLM, and then of course the user gets back a response. So this is all things that is being developed. And so Astra AI as a tool is something that has only been around for a little bit, and we've been working on it and developing it and improving it. And it's all part of sort of a research-based thing. But we are seeing some interesting results. We're hoping that this can be then worked on with future research funds. Cross our fingers. I know we all care about, we all know what it feels like to want future research funds, rather. So we're also hoping to get more research funds to continue working towards this. But what we have found so far is that Formal has, that Astra AI workflow we have been able to use with Formal, so passing the Formal repository with annotated source code to the Astra AI workflow. And then we have found that if you have a very detailed user prompt, that this Astra AI workflow can then help the LLM produce code that is out of the box compilable. Now that does come from the prompt that is very, very expert and detail written. So Damien himself, as the writer of the library Formal, wrote a very, very detailed prompt, making it very explicit what types of things need to be done to then call the Formal library. So that's obviously not going to be the average user would be able to write that detailed of a prompt. So we're hoping with future research that we'll be able to improve the workflow and continue to develop the tool so that it can be used by general users that will be writing less detailed and explicit prompts. And we're also hoping to explore the idea of production of source code as well as tests to verify the source code. and we'll explore a bit more of that. But again, a planned break. So Damien, I don't know if you have anything to add.
I just thought it might be worth adding that Kate asked me to sit here. I feel a little bit weird because I'm Kate's boss. So like, not everybody would want their boss sitting nearby when they're giving a talk, but just want you to know that I was asked to be here.
Oh yes, please. Question. I think I might be able to pull it up.
I can read it.
Does RAG run into context size limitations with large code bases? Or is that what the embeddings are supposed to help with? Sorry if I don't understand what an embedding is.
Yeah. Well, I didn't go into too much detail about what an embedding is. Does RAG run into context size limitations with large code bases? The Astra AI workflow, which uses RAG, which is just a technique, I'm not aware of that workflow having size limitations. Like the workflow will analyze it will analyze recursively basically every file in the folder that you pass it when you're passing it the repository. And then it will produce embeddings that are in this huge long JSON file. And those embeddings are basically just a numerical representation of the code itself that AI could, like the LLMs can read and understand. And then later on, the tool will also do the same process on the user prompt, and then it will compare those two embeddings, the embeddings from the annotated source code and the embeddings from the prompt, and use a cosine similarity to see which code chunks have most similarity to terms that are used in the user prompt. So I hope that explains a little bit more what embeddings are, and then I believe the answer to the context size limitations is no, at least with the Astra AI workflow. I don't know of any limitations for that. Yes, please. Absolutely. Well, yes. Yes. This one? Or was it the...
No, that was it. Sorry, go back.
Yeah.
Yeah, so it's that one bullet, Julienne unit tests annotated with metadata. Are you using the unit tests for content for your RAG system?
Yes. So actually, I'm so glad you asked that question because I very much skipped that bullet point. So I'm so glad that you pointed it out, because one of the things that we were testing is that our colleague who was focusing on using the Astra AI workflow with Amrex was more focusing on annotating the source code and not annotating any tests. I'm not super familiar with the Amrex software package, so I don't know much about what testing they do or don't have, but he was annotating the source code. And one thing that we really wanted to focus on is can the use of annotated test code improve results with using RAG, and then will it improve the final response from the LLM? Because, and sort of the whole thing that kind of pulls it together, which again, thank you so much for your question. The thing that all pulls it together, and something that we have had some good results. We're still very much in the process, as I said, with this research. So I don't want to say anything too definitive, but the reason why we wanted to look into this is because Damien, through the usage of these Fortran defined operations, we have these natural language idioms. We feel like the usage of source code or unit test code, which has, again, programming language, which can, again, it's not ambiguous because it can't be ambiguous because you have to compile it and have the machine know what to do when it runs it. So that language is not ambiguous, but it mimics natural language because of the defined operations. So we're hoping that, what we're looking into and what we're interested about is, can that combination of using programming languages, but in a way that mimics natural language, improve the results that we're getting from LLMs? Because LLMs, again, use natural language. That's how we talk to each other. But if we're passing it a lot of information, that is something that we can actually compile and check and run. We're hoping that will improve the results. And again, we've had promising results so far, but I don't want to say anything too definitive, but definitely, keep a lookout for us. Hopefully we have some more exciting stuff to say in the future. So I hope that answered your question. The answer is yes, basically. But thank you so much. Okay. So let me check the time. Okay, perfect. So how to use all of this for your project. So this next section is going to be a little bit more of a live walkthrough of how you can get started with Julienne, so that you can see what you would do if you want to go home and try testing out using Julienne, maybe for your Fortran packages. And then we'll also sort of tie it back into the idea of vibe testing and what you might do with vibe testing. So now this next part is not intimidating for me, because I don't usually do live coding examples when giving a presentation. So let's hope this goes smoothly. We'll all cross our fingers. So I'm going to switch the screen that I'm sharing and then open up my notes so I make sure I don't miss. Okay, so lovely. So here we are in the Julienne repository. So you can see that is the Git URL for Julienne. And so if you want to get started with Julienne, I suggest following some of these steps. So because I don't necessarily have a huge big software package, which I'm just going to use for this example to introduce Julienne unit tests, I'm going to start a new project to show you some of these things. And as I said, since Julienne is a FPM package and it uses FPM to then run the tests, I'm going to use a very nifty FPM function to just create a new project with very little effort. So watch this. If I just say FPM new and then name of whatever I wanted to, I'm going to name it this ISS 26-test. That now, just with that one little command, I now have an FPM project that is compilable and has the build system and all the lovely things. So I'm going to CD to that area and just show you FPM test will build the project first and then run the test suite. So just going to show you all I did was FPM new, name of what I want my repository to be named, and then FPM test, boom. Okay, now obviously this doesn't have code that does anything exciting in it, but it has all of the boilerplate, all of the setup. I don't have to write. So FPM uses TOML file. Tom's markup language? Yes. It has a TOML file, which is the basis of the build system. And I'll show you in a second how simple it can be, which is lovely. But I don't have to write my own. I don't have to manually go, Emacs, I use Emacs, Emacs, fpm.toml, and then write da-da-da-da-da-da-da. I don't have to write that all. This gives me the boilerplate, and then I can just go in and edit it for my purposes. So for the purposes of this example, I do have a fpm toml file that I made as simple as possible, because the boilerplate actually gives you a lot of defaults explicitly said, which you don't need, because if you take out some of those things, FPM has all of those defaults settings there available for you, and so you don't actually need all these extra lines of code. So I'm going to paste this in here. Okay, so now just looking at, again, just to extol the amazing things that FPM can do for you, this is your build system. So name and version are, I think, the minimum required, right? I think version is required.
Actually, this is great because, again, because we work together so closely, we can finish each other's sentences a lot. And so as she was starting this, I was like, I hope she's going to remove all that boilerplate. No, you don't need a version. Just name. Yeah, you're good.
So yeah, as you can see, very, very simple. And then I have added dependency because for Julienne, in order to use the Julienne test suite or the unit testing framework to then have a test suite, I need to add that dependency. But this is basically the build system for my current little test to show you these concepts. So that is great. And then I'm also going to copy something. So, okay, so all of that FPM new stuff, that was FPM, the FPM tool to help you get started with boilerplate stuff. So now we're going to look at the Julienne boilerplate production tool called Scaffold, which we mentioned earlier. So I'm going to copy over a very simple JSON file that we need for this boilerplate, and then we're going to, let's see, we're going to look at what the boilerplate is from FPM. So FPM has always, that FPM new command will give you this check function, but it just does nothing terribly exciting. All it does is have a print statement, put some tests in here. So we don't need it. So I'm going to remove that test file and prove to you that I have nothing in my test directory currently, but that won't be true in a couple of seconds. So just to show you and actually make some changes, the only thing that you basically need to use the Julienne scaffold program is this very simple JSON file. And the Julienne GitHub repository itself has a subdirectory called demo, which has a README, which I highly recommend reading because it will say a lot of the stuff that I've said today, but also maybe some additional details. So if you need to get started, please do read that README in the demo subdirectory. And in that demo subdirectory, you will have this test suite JSON file. So again, you can use this as boilerplate to then pass it to the scaffold program. But basically, as you can see, it's a very simple JSON file, and this specimen and widget here, those represents the each unit test collection that we're going to generate. So I'm going to change it. And this boilerplate is also based upon the presumption that you have modules named in a certain way. So if you are trying to integrate Julienne into your project, I would recommend using this boilerplate, using the scaffold program to produce the boilerplate, and then just going in, and you'll have to do some renaming of stuff, but this will still be very helpful. But because we're here at NCAR, and because there's always discussions about what is the difference between NCAR and UCAR and UCP, I figured that for this example, I will update this JSON file just to prove to you that you don't have to have the example that's in this JSON file from the repository, which with widget and specimen, you don't have to have that. You can say whatever you want, and you can add stuff. So there were 2 things before, now there's 3, NCAR, UCAR, UCP. So I'm saving this file, and then I'm exiting. And so now I'm going to use the scaffold program to generate the boilerplate to get started with Julienne unit testing. So this command is a little bit long, but all of this is online in the readmes and such, so don't worry, you don't have to memorize this or anything, but you do fpm run scaffold, and then you have these 2 dashes, which means you're now passing flags to fpm, not to the compiler. No, I got that backwards.
Right, the double dash is where you arguments that are going to go to the program that you're running, as opposed to arguments for FPM.
Ah, okay, that's the right way to say it. Thank you. Yes. So then now I'm going to use the -JSON flag and pass it. Oh, let me actually, I need to CD up one. So now I'm passing it the path. So JSON file, that flag means I just need to pass it the path to where that JSON file is that we just looked at. So I'm going to do that. And then we need to, the only other argument that you need for the scaffold program is suite path. So it is pass, so you need to pass the path to the test directory where you want the generated tests to be. So at the moment, as I showed you earlier, there's nothing in that test directory, but we will see that change soon as long as I spell everything.
One nice thing with FPM is that you can run it from anywhere inside your source tree. So the reason Kate had to go up was to make it simpler for writing the JSON file. She wouldn't have to include the double // in her path.
Well, the reason why I had to go up is because the directory I was just in before is an FPM package.
And I was wrong,
so if I did
sorry.
FPM run.
Be quiet. This is why you don't want your boss sitting here while you're giving a talk.
No, I'm very happy to have David. I think, as you can tell from his comments earlier, we get along really well. So I'm more than happy to have you sitting up here, not at all nervous, and very much is a help. So thank you so much. But yeah, we have to run it from the Julienne place because Julienne is the one that has a program called Scaffold. So if you run it from a subdirectory that is not an FPM package, then it would work. But because the subdirectory is an FPM package as well, then this would have not the expected results. So I think now I'm just ready to run. And that was very quick. Just a couple of output messages saying that it read the information from the JSON file and it wrote the scaffolding, what I've been calling boilerplate, to that directory. So now let's go in here and ls that directory. It has stuff. So it has a driver, and then it has 3 other files. And those 3 other files are representing the content of what I've been calling the unit test collection. So in ncar_test_m.f90, that is a unit test collection. And then inside of that module, there are individual functions, which are the individual unit tests, as I've been saying today. And then the driver runs it all. So let's just look at the driver really quickly. So this is the driver. And again, you don't have to write any of this yourself. You can just edit stuff once you generate this with the scaffold program. But basically, this is just how everything gets packaged together and then run correctly. So you can see here that there is an array. Well, as I hope you can see. Maybe not everybody's a Fortran programmer, but I think you can still see that there are multiple things called test fixture T. So that is an array with multiple test fixture T. And then you can see that there's the NCAR test, the UCAR test, and the UCP test. So if you wanted to, first of all, if you were using this to set up Julienne unit tests for your software project, you would just go in there and do renames for whatever you might need to rename. But if you used the JSON file correctly, then hopefully these names are not too dissimilar to what you would need. But what if you just then want to add a new unit test collection? All you have to do is just add another line to where those test fixture T objects are, create a new test fixture T, and pass it the name of the test that then you have hopefully written elsewhere. So then that just expands your collection of unit tests. So that's the driver. And now that we're doing this sort of live demo, I mean, the questions have been obviously welcome the entire time, and thank you for everybody who asked questions. But again, just as a reminder, now that we're doing the live demo, please do stop me if you have any questions or if I'm going too quickly through something that you want to understand better. So now, I think now we're ready to run the test suite, because we have, let's do the tree command and just see what we have. Oh, well, we also have all this build. We'll ignore the build. We have an FBM TOML file. We have a README, which again, this was just generated boilerplate. And then we have our tests here, which were generated by the scaffold program. So let's see what happens if we try to run the test suite. And again, all you have to do for that is FPM test. An error, but 'tis expected. Because if you go into Julienne and you go into the demo subdirectory, and if you follow the instructions in the README there, you will automatically have modules that are named the correct thing that are expected by that specimen and widget that I had earlier. So the scaffold program generated unit tests for things related to the names that you put in the JSON file. So if you do all that in the demo and follow those instructions, it will all be working better than it did here. But because I renamed stuff for this, again, this lovely context that we're at here, it failed because I don't have a module named ucar_m. All that boilerplate of the unit test that I generated expect a module called that, and there is none, so that's the problem. But I did prepare for this, so all I have to do is copy this into my source directory. Oh, I should have done all of the _m files that are there are what I want. So now if I look at my source directory within the FPM build structure, we have ncar_m, ucar_m, ucp_m. So now let's try running FPM test again. Compiling. Haha, we ran a test suite. So we just ran a Julienne test suite. And now we can then peek into what the results are. So as we have explored earlier with our different use cases, this whole bit is the reporting from the tests from one unit test collection, and then this whole bit is another unit test collection, and etc. So here we have NCAR and UCAR and UCP. So if those were names of derived types in your software package, then that indicates that all of these tests are testing the NCAR derived type and etc. So since this is all boilerplate, this is all on purpose to show what it looks like when you have pass and a failure and a skip, which we have referenced but not really talked about yet. So the NCAR boilerplate stuff that we have passes on doing something, terribly exciting, but then it fails on checking something. Oh no. But luckily, because Julienne gives you some diagnostics, we can see that this test that checks something expects this value within a tolerance of this, but the actual value is this. So now you're seeing what the boilerplate actually is within that that the scaffold program sort of works with. Is the boilerplate is all related to just pi, right? And so we then, and it's, again, the boilerplate is the same for all of the different tests that I created. So all of these are essentially the same. So the distinction is not necessarily exciting, but point is that when you're writing your Julienne test, you just go in and replace the boilerplate with all the different things that you actually want to test. But for the purposes of this tutorial, let's try and get some stuff to pass. So, well, first of all, let's look at the source code for our NCAR, NCAR module. So that is there. So as you can see, it just has an NCAR type with one type-bound procedure called pi, because again, that's what all this boilerplate is sort of set up. And then it just assigns a value to pi, and that's all it does. So then why is it failing? If we scroll back up to our diagnostics, it's failing because of the tolerance, right? If you look at these two values, they're not terribly dissimilar, but the tolerance is the issue. So that means we need to go into our test. So if we go into our test and look at the NCAR one first, I'm going to skip to approximates because I know that, so this is where the check something test is. And you can see that the test diagnosis is all, and then it has an array constructor there, approximates NCAR pi within, and then it gives the tolerance. So we're gonna relax that tolerance a little bit, save the file, and run FPM test again. And you can see now, if I scroll up, ta-da, now we have a NCAR passes on doing something, and now it also passes on checking something, which is fabulous, but it still skips on skipping something, which the description of the test is skipping something, so it does seem to be doing what it wants to do, but I'm going to show you how you test skipping, or sorry, how you skip a test, so that then you can see how not to skip a test, or skip it if you want to. Anyway, so again, just focusing on NCAR, you see that now we have 2 or 3 tests passed, 1 test were skipped, and these other ones stayed the same, but they're all, again, the same boilerplate. So we're gonna focus on the NCAR one at the moment. So going back into the NCAR test, we're going to go down to this skipping something. So here, so this, oops, this whole array, so this is an array constructor with 3 different values. So this array is the array of each individual unit test that makes up the collection. So the first line on line 28, we have the doing something test and the description. Then you have a character string which describes that test, doing something. And then you have the checking something test, and then you have the skipping something test. But does anybody notice the difference between the check something test and the skipping something test? I don't know if it's the most legible, but yes, haha, thank you very much. This is very true. That is the correct answer. It is the number of arguments to the constructor of test description T. So that is how you skip a test. Now, another prescient question is, why would you skip a test? Because we love tests, as we've all talked about today. Why would you skip a test? Well, you might skip a test if you're running into compiler bugs, and we've all run into compiler bugs, I'm sure. And so if so a lot of our software we try to run, we have CI set up to run with multiple different compilers, also multiple different compiler versions, so that we are testing the breadth of what any of our users might use with the different compilers and versions that they have access to. So if there's a known compiler bug for a specific compiler for a specific version, you might want to skip that test so that it doesn't fail, because it's not necessarily failing because your package is doing something incorrectly. It's failing because of a known compiler bug. And that compiler bug could be causing a compile time error or a runtime crash. Either way, you might not want to run that test with that specific compiler/version. So the way that you do that then is you just change the number of arguments, as we have stated. So you take out, and the argument that you take out is the name of the function. So here for this test description T object, you have a string which describes the test, and then you pass it the name of the function. So here you can see do something, well, let's focus on check something. There you can see that the object is being constructed with the name check something. And then if you look right here at line 34, you have check something. So then that's the unit test that will be run for that test description. And there is no skip something test, but just for the purposes of, okay, correct, yes. Just for the purposes of this example, let's make the skip something function, unit test, and then this is also how you would add a unit test. If you want to add a unit test to unit collection, you would just define a new function, and we want to make sure that the name is the same. I think it was skipping or skip. It doesn't matter. I get to fill it in myself. So I'm going to say skipping something. So you just name the function, and then you have the result be a type of test diagnosis T. It could be named anything. And then you have it assign something. So I'm just going to assign it the value true, and then it will construct an object that tells the test diagnosis that it passed. So that is always going to pass right now. And then if I exit and do FBM test again, now we have the NCAR unit test collection that has 3 of 3 tests passed and 0 tests were skipped. So that is the skipping functionality. But just to show how you might do this is that if there's a specific compiler that is causing the bug, you might do some macro pre-processing stuff here where you have this line 30, which runs that skipping something test. You only have that run with compilers. Well, you have a macro that says if compiler that is causing the issue, then you have a line where it has a test description T constructor that does not have the final argument, which passes the name of the function, and then else have it where it does pass that, and then so that means that all the compilers that can do it will run the test, and the one that can't, it will be skipped. So that is how we do that in our test suites, where that is definitely unfortunately necessary because compiler bugs do exist. I'm sure it's not a shock to anyone here. So let's see. Okay, so that is a lot of what I wanted to show, but there is another functionality with the FBM, or the Julienne test suite rather, that I wanted to show, which is filtering. So imagine a scenario where you have a unit test suite that is quite long, because maybe you have, again, sort of based on this idea, if we're using Julienne to test different drive types, if you have, say, 20 different drive types in your software that you want to test, then you might have 20 different unit test collections. And in that unit test collection, you might have a bunch of unit tests per collection. So that could be some pretty long output, right? But imagine you're only working on making some changes to one particular drive type, and you don't really want to have to look through the entire output because you're only touching specific parts of the code. You might want to then only run certain subsets of the test suite. And that is what the filtering functionality gives you with Julienne. So how you do that is I'm going to just run the NCAR one, because that's the one that we just updated to then have 3 passing tests. So I'm going to say FPM test -- and again, that -- is now passing these next flags to the program, not to FPM. So we have then the contains flag, and then you just write a string which is related to some of the characters that you put in the description of your different tests. So since we have the NCAR test named NCAR, let's just see what happens now. So you can see it still does print out some output related to the other unit test collections, but it just says 0 for everything, and it doesn't give you any more output than that. But the main part is that you can focus on just that one unit test that you wanted to focus on. So if I'm iterating on work on that one, I just filter out that test, and then I can only run that and then see, okay, my changes are or are not making my test fail. But then just as a friendly reminder, of course, before you push anything to any like remote Git servers, please do run the full test suite, because you never know. So this is just sort of to help iterate with development, but you do always want to run your full test suite before you make any significant push anything out really. So I think that is I think that is the totality of the live walkthrough that I wanted to do. So I will ask Damien if he has any additional things to say based on what I just. Nope. Okay, great. Well, then let me go back to sharing my presentation slides and just say that when these slides are uploaded, like when I pass these slides off, they will have some sort of hopefully helpful bullet points that kind of describe textually the live walkthrough that we went through, but also I believe there'll be a video of this. So either way, hopefully there'll be stuff for you to look at later if you do want to try playing around with any of this stuff. And if you do ever run into any questions with Julienne, of course, again, I'll remind everybody for the 5 millionth time, please do contact us. Okay, so those are just some helpful things that we discussed in the live walkthrough. So now back to vibe testing. Can you try vibe testing? Well, the answer is I am because ideas around how to use unit tests within LLMs are still developing. As I said, I believe Damien's the first person to use the phrase vibe testing, and so it's something that we're kind of exploring within some of our research projects, and hopefully we'll be able to continue exploring. But another answer is yes, because the Astra AI workflow that I mentioned earlier, that is now publicly available. So if you do want to play around with that, you can feel free to. That's at that GitHub. But please do note, it is a research project that is still in development. So, there may be some little things here or there, some little snags or edge cases that you might run into, but you can play around with that if you want to do some of the things that I described earlier that are possible with Astra AI. But then also I wanted to say that maybe you can do that in general, because even if you're not using sort of an AI tool that uses RAG techniques under the hood, you can also theoretically copy and paste source code yourself into your prompts. And if you're using source code that uses natural language idioms, such as the ones we've described today, again, we're hoping that can maybe get better responses from the LLM, but also just be aware that you can, again, copy source code into your LLM prompts. And if you're doing tests, hopefully that can, if the tests are verified to test code that performs things in a certain correct way, maybe that unit testing thing can be better information to provide to the LLM than some source code code chunks even. So if you do want to try out this sort of new concept that is in flux and development of vibe testing, feel free to just directly copy and paste some stuff into your LLM prompts and see how that goes. So just to sort of wrap up that idea, as I've mentioned today, Julienne has these natural language idioms that help you write unit tests as specifications. So if you do use Julienne unit tests, then you have these unit tests that mimic natural language, and that then can be used to supplement LLM prompts. So please do consider how you can use, well, first of all, consider writing unit tests if you don't, or considering writing more unit tests if you do. But then also consider how you can utilize tests to improve responses from LLMs, and feel free to, again, contact us if you want to talk more or collaborate on the idea of vibe testing. We'll see where this all goes. But also remember the test-driven development that I mentioned earlier. If you want to try this idea of vibe code testing, one potential thing that I could conceive of is that you do test-driven development where the human is the one writing the unit test. So you have the unit test that you need it to pass, you have the test written as a specification that can only pass if the source code does it correctly. So you write the unit test first, and then you provide the unit test to the LLM and say, please write source code so that that unit test will pass. So the human then is involved in the sort of very important first step. Then you pass it off to an LLM, and then I'm sure there's probably going to be iteration needing to happen before that unit test can pass. But if you start from that test, maybe that's a way to use LLMs with developing code in a way that is a little bit more verifiable as far as what the LLM is producing. So yeah, just please consider all of these ideas and how they might impact you and your workflow. So that is the end of the main part of my presentation. And as I said, I always like to end with just a little public service announcement about how Fortran is doing great stuff out there. And if you want to learn more about various Fortran communities, you can follow some of these links. So I like to have this slide, which is a grab bag of Fortran tools, because there's a lot of people that have to interact with Fortran because they work on a project where there's some legacy code that is written in Fortran. But if they're not sort of like a Fortran programmer that is involved in the community of Fortran developers, they might not know that there's a bunch of tools that are out there for Fortran. So there's this thing called Cody, which I actually talked about at lunch the other day. And so please do check that out. It's a static analysis tool for Fortran and C++, or C and C++. So if that sounds interesting, please, you can find more information there at their website. And then I also have linked some tutorials. Then there's also a bunch of useful tools like a Fortran linter and ROGFF, return of JSON for Fortran. It's a utility related to JSON files in Fortran. Isovarying string, all of these, I won't go into detail, but you can click all of these links later if you're interested. Here's some more of that grab bag. And then at the end, I have a grab bag within my grab bag. So there's this user on GitHub, which has this repository, which is just a repository of like a text file that has a bunch of links to all of the Fortran tools that this user has ever encountered on the internet. So this user does not verify the veracity or loveliness of any of these tools, right? Use at your own discretion, but it is quite an extensive list, and I think this person is relatively good at keeping it up to date. So if you want to just poke around at any of those things, please do look there as well. And then I always like to do a little announcement about upcoming Fortran features. So Damien has already mentioned some of these things. The Fortran 2028 standard is coming up, well, hopefully 2028. And there will be generic programming, which will provide type-safe templates. There will also be some asynchronous collectives. Did that get in? Yes, asynchronous collectives. And actually, I just realized that I did make a mistake in this slide. The standardized Fortran preprocessor there's been a lot of work on that, but actually, unfortunately, will not make it into the next standard. So I need to update this slide. But look out, hopefully, for a future standard. And just as another thing that I usually like to say when I'm talking about Fortran a lot in my presentation is that if you're a Fortran user and if you care about the language and you want it to continue to thrive, please do consider joining the Fortran Standards Committee if that seems like something that you might be interested in. Because if you want the Fortran language to have certain features that it doesn't currently, it can, right? If you get involved, or if you establish communication with people that are on the standards committee, you can talk to them. And if you find somebody on the committee that can advocate for things that you want introduced into the language or updated in the language, that's also a way to do it. So just do be aware that as a user of a language, you can still have an impact on the language itself if you get involved yourself, or if you get involved in close communication with somebody who's on the committee. So do think about it if that sounds appropriate for you. The international body is WG5, and then the US national body is Insights, but commonly known as J3. So feel free to follow any of these links or contact us if you have more questions about that. And we're getting close. I also just have this slide to say that there are that Fortran is a much more active community than I think a lot of people think. And so if you haven't heard of fortranlang.org, and if you're a Fortran user, or if you have a student that doesn't know anything about Fortran but needs to use Fortran in a project, so they need to come up to speed, if any of those things are true about you, and you don't know about that website, please do check it out. It's a really great website. It has a bunch of tutorials, which are really great. It has links to playgrounds and has information about compilers. Has a bunch of different helpful information, and then also has link to LFortran, which I mentioned earlier, which is both a compiler and an interpreter. So the interpreter part you can play around with a little bit, might be easier for students to sort of jump in. And then there's also a Fortran Lang discourse, which is super active, I think, at least compared to what I maybe expected when I first encountered it. So if you're a Fortran user and you have questions, please do post them on this Fortran Lang discourse. Hopefully you will get some good responses. If you're a Fortran user and you want to answer people's questions, please do become involved in the community by also answering questions. And then there's a couple other links. If you want to know more about what we do at Berkeley Lab related to Fortran, there's that helpful webpage that will tell you more about us. And I would also like to acknowledge that this materials-based fund work supported by the US DOE, Office of Science, Office of Advanced Scientific Computing Research. And then also just, again, I mentioned this earlier, but Brad Richardson is the lead developer of Veggies, which is the software project that Julienne was originally inspired by. So I also want to acknowledge his work. And with that, I'd like to say thank you very much. Thank you for bearing with all of my little breaks for water. I desperately appreciate it. And yes, any questions?
So we've been adding a lot of we're trying to increase the amount of unit tests we have in our code, but mostly we've been using, and mostly just because we started this before we knew about this, was PF unit. So I was just wondering, could you, it may be too big of an ask so we can talk about it afterward, but just compare and contrast a little bit PF unit versus Julienne, sorry. Yeah, how are you?
Julienne.
Yeah.
Any pronunciation is fine of Julienne. So I have not myself used PF unit. I do know that it is like a very widely used unit testing framework out there, and we actually know pretty well Tom Clooney, who is the lead developer on that. He's on the Fortran Standards Committee, and he's a great guy and really incredible. Has lots of great software. So I've heard great things about PF unit. I can't personally speak to comparing and contrasting, but maybe Damien can do a little bit more of that.
So yeah, I know Tom really well, and he is one of the smartest people I've ever met.
Oh, he's online.
Is he?
Hi.
I just saw him in Zoom. That's so lovely. Hi, Tom.
Oh, you're listening. So I would say I think the learning curve for Julienne is probably shorter, less steep, but I'm sure it doesn't have anywhere near the capabilities that PF unit has. So I did some work for Tom on porting PF unit a decade ago, so I also have to say that my knowledge of PF unit is ancient and minimal. It was a pretty small project. I was working on porting it to the Cray systems for him.
Cool, thanks.
Tom, I don't know if you were talking. I don't think we heard you in the room. Were you speaking?
I was not. I was waiting. Can you hear me now?
Yes.
Okay, so I can only say a little bit. I also don't really know Julienne except for this presentation, which I only got to see parts of in similar presentations before. Certainly a lot of overlap. I think one of the big differences, and something that I had tried to add to PF unit but didn't get nearly as well done as what is in Julienne, is this natural language stuff. In PF unit, when I made the attempt, I was following a pattern that was used in other unit testing frameworks called Hamcrest. And Hamcrest is based much more upon object-oriented techniques of extending base types rather than using these operators. But because Fortran is single inheritance, it turns out to be much more limiting than what you get with the operator approach. And if I had to do it all over again, I would certainly do that. I think one of the other big differences is just simply that PF unit is much older and so has legacy baggage in terms of things that it has to support. And writing it all over again. If I had to start over right now, from what I can see right now, I would go to Julienne. I don't think there's a good conversion path though from my thousands of unit tests I have in my group to switch over at this point. But I can easily see somebody starting from scratch. A lot to be said about going down the Julienne approach.
One other thing I'll mention, so Kate mentioned that Julienne was inspired by veggies, and what the problem I was trying to, so you might ask, why am I not using veggies? Because veggies is also great software, and I really liked the approach in veggies. And there were some issues with portability at the time that I started working on Julienne. Veggies wasn't supporting the Intel compiler, and I really needed the Intel compiler. And so I actually started by writing, and I'm really into minimalism. So I was like, okay, I don't really use that much of veggies. What's the smallest utility I could write that would just give me the thin slice that I use? And it really was only a little over 100 lines is where it started. But then what happened is that over time, as I was waiting for the Intel support in veggies, Julienne, of course, started to grow. And it was actually when we came up with these idioms, these, defined operations, that I started to realize, okay, this is useful in its own right, I guess.
Thanks. I just want to say thanks, Tom, for your input.
Yes, thanks, Tom, so much. And I just want to say, there's room for multiple unit testing frameworks out there, right? So definitely look into these various things that we've mentioned, Julienne, veggies, PF unit, and whatever works for your use case. We just love having more unit testing out there to verify the software that we're using. But yeah, thank you so much, Tom, for joining in. That was really fun.
I have a really basic question from something way in your early presentation. So it was when you were talking about the neural network.
Yes.
And it was the test before that.
Okay. So we are at caffeine fiats. Was it around here?
Yeah. Go back. Yes. So in your tolerance there, why do you have a tolerance on a logical? I would think a logical is either true or false. What's the tolerance doing?
Yeah, that's a really good question. So, neural networks are generally working with floating point numbers, right? So basically, if you go to the Wikipedia, okay, let's go all the way back. When I first started working on fiats, I actually didn't have a plan to write my own deep learning library either. Where it started is when I went to Berkeley Lab 5 years ago, I had no experience with deep learning at all. And so I actually had a student working with me, and we spent time at a whiteboard just propagating signals through a simple neural network by hand, right? Just to kind of develop some intuition about what it was doing. And so I started with, if you go to the Wikipedia page for feed-forward neural network, that Wikipedia page has this little single layer, one hidden layer network with 3 neurons or nodes in the layer, and it's representing an exclusive OR gate, an XOR gate, right? So then if you look at the unit tests in fiats, a lot of them are like digital logic gates, because that was just kind of where I started. But you're working with floating point numbers. So I'm using 0 as false and 1 as true, but I'm not going to get exactly 0 or exactly 1. Yeah.
Okay, thank you.
Thank you.
If you're in the CMakes, CTest, CDash realm, how does these tools fit into that universe, I guess? Or do they?
I don't think I would characterize that they do fit into the same universe. I don't know if you agree or disagree, Damien.
I would say they're pretty different. I say CTest is there to run your tests for you. And at least in my uses of CTest, which again goes back a ways, most of the tests each test would be a separate program. This is more of so there's a definition of library where a library has code that your code calls, whereas a framework calls your code, right? So what makes Julienne a framework is that you're going to write all these test functions, right? Whereas CTest, all it's really doing is running your code. And there's not a lot more functionality than that. I will say the one really nice thing about CTest is it can run tests in parallel, which is what we can't currently do with Julienne. But otherwise, there's a lot more here, and it's not giving you like the expressions that you saw. It's not, so when you write these expressions like X approximates Y within tolerance, what's happening there is if that fails, you're going to get a diagnostic message that's just been packaged up for you. Or a better example is maybe I equals expected J. So as Kate mentioned, there's an implicit asymmetry there. That's one reason why we don't just use the equals. The asymmetry is that, if I say I equals expected J, which one do you think is the expected value, I or J? Anybody? J, right? So hopefully that's intuitive. The one sign that it's intuitive is that people can guess what you mean. And so what's going to happen is Julienne is going to take advantage of that asymmetry, and when it writes the diagnostic message, it's going to say, oh, you expected this value, but you got that value, right? So CTest isn't doing that kind of stuff where it's like packaging up useful diagnostics for you.
Right. You can't couple it. You can't say from the CTest to buy into your framework and then report those back to CDash or something like that.
You certainly could. I mean, again, since CTest is really just running your tests for you, it could be running your Julienne tests.
But I would say that we haven't tested that. So there could be some sort of hackiness that you might need to get that to work. We haven't tested that, but I would also just say, as far as like kind of a weak analogy, that CMake and CTest, FPM is kind of your CMake, and then CTest is kind of your Julienne. But that is a weak analogy, and there are significant differences, like Damien said. But I also, I see we have another question in the room. But before that, I think I saw that Tom Clooney had his hand raised. So maybe Tom, if you want to say.
Yeah, if I could comment, the pattern that I generally come up with here is each of my major test suites I make into a C-test. And so then I've got a project that doesn't know anything about my unit testing framework. When somebody runs C-test on that, it's going to get all of my tests run, and it will tell them which of the different suites break. And if they do verbose, then you're going to see all the kinds of output that you're going to get, the more detailed stuff that the unit testing framework is designed for. And that same pattern should work very well with any unit testing framework, including Julienne.
Thanks.
Yeah, no, I appreciate that input. And then in the room, I think we had.
Thank you. This was fantastic. I have two questions, basically. One is, have you considered contributing FPM as a build tool to SPEC?
So I'm pretty sure you can build FPM with SPEC.
I checked that. Yes, you can.
Okay.
But the other thing is, CMake package is a thing. It's a package that defines, okay, this is a package you build with CMake.
Right.
And this is dependencies and so on. So it should be fairly simple if from looking at how this works, to define an FPM package as a class in spec and then say, okay, this is an FPM package. And then all you do is spec install Julienne. And I know you can do it with FPM as well, but then you can build it together with all the other tools in the same system.
Okay.
I misunderstood. So were you asking us to make Julienne a spec package? Is that what you?
No, I was asking if you had thought about the idea of providing that capability to spec to run FPM packages, install FPM packages.
So the answer is no, or at least I haven't thought about it. But I would say that I think the idea is very compelling, and there are some other projects that I'm working on currently at Berkeley Lab where I'm going to be poking around SPAC a bit more. And so I'm glad that you mentioned that, because when I'm poking around for those other purposes, I might try poking around something like that. But I'm not one of like the lead developers of FPM, so I would probably want to contact them and because they would know more about maybe they would know more about the FPM context to then maybe integrate it more. But I think that's a very compelling idea. And then I don't know, Damien.
I would say that in practice, like in theory, FPM and SPAC are pretty similar, but and so I could see where that could make sense. But in practice, they're a little bit different, and it has to do with the fact that FPM grew out of the Fortran community itself. So I think SPAC is largely it's especially useful for system administrators who want to keep a consistent software stack with sometimes different versions of the same package or what have you. The way that I learned to use FPM was from Brad Richardson. So let me give you a little bit of history here too. So my understanding is that Andrei Certic, when he was at Los Alamos, invented FPM. He was writing it in Rust. Brad liked what he was doing, but didn't want to write it in Rust. Brad decided to write it in Haskell. The whole Fortran community liked what Brad was doing, but didn't want to work in Haskell, so they rewrote the whole thing in Fortran. So depending on how you look at it, there's multiple inventors of FPM, but I learned it from Brad. And with Brad's approach, you very rarely type FPM install. You normally just build things in place. And so the very notion, that's where I'm saying it's kind of different in practice. I hardly ever use it to put something outside of my source tree,
But I would say that we do interact with scientists that want us to help them with their build systems where they do actually care about like having an install. So I'm at least interested enough to poke around.
Me too. So we can...
Okay, great, awesome. Yeah, we could just stay in contact.
Completely different. Was there anything else in the room? No. All right. Second question, completely different thing. As you know, we have a lot of legacy code in Fortran, and no test for it because things were done differently in the past. Have you explored the opposite way of the unit test of the LLM-driven development cycle, where you just give the LLM the code and ask it to write unit tests, and then hopefully we've got still enough understanding to make sure that the unit tests are also doing something useful with that? Because nobody likes to write tests for legacy code where the original developer is sitting in the Bahamas and is celebrating retirement.
Yeah, so we haven't done that yet, but that is something that we've been talking about doing. So most of what I talked about as far as directionality was like test and then using the LLM and then the test can be used to verify the output of the LLM. But something that we have talked about, again, we're responding to proposals right now, so we're thinking a lot about like what are our next steps in our research projects that we might want to do. And that is one thing that we did talk about exploring is if we are able to, we would love to explore if we can use LLMs to generate generate tests from source code, and if those can be tests that are like useful and that produce things that can actually verify code in a way that is verifiable, like that the tests that are produced are verifiable and that they actually do verify the source code that they were asked to test. So that is not something we have done so far, but that is something that we're definitely interested in. So who knows, the future is yet to be determined. But thank you so much.
Thank you.
Thank you. Any other questions? I don't remember if I was to end at 3 or 3:10, but 3:10. So time for more questions if there are. Oh, there's an online question. Thank you. Let me see. Okay, so I think, yeah, okay. So the online question says, I've done that with Python code and it works great. Using RAG with pfunit/Julienne would help an LLM write Fortran tests, I think. Okay, interesting. Right, so I think that's what we were just saying is that this person, Sam Rabin from online, said that they've done they've done what we were just discussing with Python code. And so, yeah, potentially it is something to explore that could also be successful if we do that with Julienne or PF unit tests and using RAG and LLMs. Great. And then the other comment was, given that there is much less of training corpus in the LLMs for Fortran tests relative to Python tests. Yes, I'm sure anybody who does use both Fortran and LLMs would probably already know that there's definitely much less training data out there for Fortran than there are for some other languages. So yeah, that obviously impacts the results, but hopefully with things like, RAG techniques and stuff like this, and maybe what we're doing with vibe testing, hopefully that we can still improve the responses. And then we have another comment from Catherine Deward. I've done that on a code base that had a motif GUI C++ for C++. It successfully let the LLM generate a Qt GUI. Okay, so there's that comment from online. So yeah, this seems to be something that people are thinking about, which is great to know.
One more question about, to go back to the vibe, I think you missed one negative of vibe coding, is that going back to the licensing, I don't think you can license vibe code, right? That it's not considered human authored, so.
No, yes, I really appreciate that comment. Yeah, that pros and cons slide for vibe coding was just one pro and one con. And I certainly think that discussions around things like vibe coding can go into many, many more topics. So I do appreciate that, because that is a very significant con. Yes, the issue of authorship and being able to do that copyright and whatnot is very complicated, and it's something that exists with all usages of AI across our society, not just our industry. So yeah.
There is one big upside to that with the DOE labs, and I imagine most other labs, when you're putting software out there as open source, there's an approval process to go through. And yeah, I think you see where this is going. I have a collaborator who's working on some code where he's having the LLM write every line of it, specifically because it shortens the approval process. He submitted the form at Los Alamos for this, and you have to list who authored the code, and he put Claude, and it just got approved really fast because it wasn't written by anybody at the lab.
Yeah, I think the way that our systems, as they were set up before we had AI and LLMs, really with the capabilities that they are nowadays. I guess what I'm trying to say is we're seeing how our systems that were developed before AI and LLMs are being impacted by this huge, quick jump. And so something like that sounds quite curious to me. But yeah, all of these things are definitely in flux, and yeah, these systems are not necessarily able to change as quick as the pace of AI and LLM. So yeah, we've heard a lot of topics, or a lot of discussion within these presentations this week about AI or LLMs and usage of them, and some are sort of more pushing the usage of them, some are very much suggesting not to use them. And so at least for me to state sort of my opinion, as I would say, use with caution is sort of my brief summary. But yeah, we all have very different opinions and experiences related to this, and it's always changing. Any other questions? Okay, great. Well, please. Oh yeah, okay. Well, I'll just say thank you for being such a wonderful audience. Thank you very much.
Cool. Yeah. Thanks, Kate and Damien. Appreciate it. It was great. This is actually the last talk for the day. I know there was one more, which was mine, but as chair, I canceled my own talk. So I had that privilege. But yeah, I just want to say, again, just a reminder, if you are interested, there's a social at Rayback Collective, which is within walking distance. It's about 20 minutes away, where they have a couple food trucks and, drinks and stuff. Otherwise, yeah, we'll be starting again tomorrow here at 8:30. And tomorrow we're jumping straight into talks, and we'll go until lunch. So